always people trickling in these morning sessions. So I'm Ben Root. I'm thank you. Oh, awesome. Thank you. I'm Ben Root, and I have stickers. So, woohoo. Oh, yeah, that's nice. I like that. Put that right there on the back of my laptop. Yeah. I'm Ben Root. I am one of the developers for Matplotlib. Joining me today, helping out, is Joe Kington. And Jen, I have no clue how to pronounce your last name. Sorry, Jen. Both these guys here are also very active members of the Matplotlib community. Jen recently became a regular developer. Have we given you commit rights yet?
No.
No?
I actually don't commit that often.
Okay. I'm really, you'll find me a lot on the mailing list and doing a lot of the code reviews. Joe here, he's the one getting a whole lot of karma points on Stack Overflow. I have like 12 karma points. He had like 50,000. So most of the questions on Stack Overflow about Matplotlib is answered by him. So also, as a shameless plug, I wrote a book, Interactive Applications Using Matplotlib. It has nothing to do with this tutorial. And matter of fact, if you are brand new to Python, it probably is a little bit advanced for you at this moment, but feel free to buy it, and then, maybe in a few months as you start to understand Python a little better, and you feel like you want to make, your own GUIs and such, perfect book for it. So please, I really put a lot of effort into this book, probably way more than I should have. So I really like it. And my mom says it's great, so.
How are your reviews?
Do I actually have any reviews yet? No, you can be the first to review this item. Please be the first to review this item. So is anyone having trouble getting the notebooks downloaded? I put some final updates and stuff. There was a couple bugs I found on the plane ride in yesterday, so didn't know. If you had the version that was there, a couple days ago, you're going to have most of it. It's just there's a few bugs I had to fix. So we're all good to go? All right. Yeah. By the way, if you have any questions, I'm not going to see your hand waving, so just shout out, and we'll help you out. Okay? So if you start up your IPython notebook, in the directory that you unzipped the contents of the repository from, you'll see this wonderful listing of IPython notebooks. We're going to skip part 0. That's basically meant for, I originally wrote this tutorial for my coworkers, and so they needed a crash course into NumPy, so I put in that part 0 there. So we're going to go to part 1. Just click on that, and we'll get started. All right. By the way, I accept pull requests for fixes to this notebook. One of my first pull requests for this tutorial was last year, and someone said, hey, it doesn't work in Python 3, because I had like 2 print statements. So someone sent me a pull request to fix that, and that got accepted within 10 seconds. So I'm more than happy to accept pull requests to improve this tutorial. All right, so what is Matplotlib? Well, I hope you guys have at least a clue what it is since you're here. It is the plotting library, the core plotting library for Python, particularly designed towards producing scientific publication quality plots, but it also has other uses as well, such as producing interactive applications for scientific visualization. So if you need to plot something in Python, Matplotlib, even if you're not using Matplotlib directly and you're using some other library like Seaborn or Pandas or something like that, Matplotlib is running all that underneath the hood. So we are the library to do this and been doing it for about, 15 years now almost. So it's, that's what you want to use, and that's why you're here. Our documentation's on matplotlib.org, a nice little web page where you can find out all sorts of stuff about the library. It is the place to go to find information, documentation, and as I'll cover, the gallery. The gallery. A lot of questions come up on the mailing list is how do I make my plot look like this? And these are the sort of questions you really can't ask on Google. You know, how do I make my plot look like this, to have that with it? So you either ask it on the mailing list or you go to the gallery, which is basically what we call the poor man's search, image search. And what's nice with the gallery is that it's organized and it has a thumbnail of many, many different examples of what you can do with Matplotlib. None of them you probably actually want to use directly for pretty plots, but it will show the individual features. So you can see how to do bar plots. You can see how you can have multiple plots in a figure, how to do histograms, how to display images, how to have like ridiculous images that color mapped and all sorts of things. And so you can go and pick and go to any example. You go to any example and it will take you to the code example and you can see how that example was produced. See how to do pie charts, all these things. So the gallery is a really good place to go, oh yeah, I need to have that feature. How did that done? Oh, how do I make the background black? Or how do I do all sorts of things? This is where you go. And if you want some health information, the day I realized I could cook bacon whenever I wanted. Yes. All right. And as I mentioned earlier, there is a mailing list. And we answer a lot of questions there. And then there's also Stack Overflow where Joe will answer your question. We're hosted on GitHub. And we accept bug reports, feature requests. Matter of fact, just the other day, we finally got our pull requests down to under 100. Very impressive. When you submit a bug report, there's a few pieces of information that we always want to know. What version of Matplotlib you're using, and which backend you're using. What is a backend? Well, one of the things that made Matplotlib so successful is that Matplotlib will work no matter which platform you're on. So you're on Mac, Windows, Linux, it will work. And it doesn't matter which GUI toolkit you're using. If you're using GTK, if you're using Qt, if you're using Wax, or there's a bunch of them. We work with pretty much all of those GUIs. So, but the thing is that some bugs can be very specific to a backend. So we need to know your version and which platform you're on and also the backend. So a good way to get that information is to run these 3 commands. So I'm running a near recent version of Matplotlib, so it's the dev version, and I'm using the Qt4 ag backend. Sometimes also you need to say whether or not you're running it in an IPython session or whatever, but we'll let you know if there's something needs to be more specific. because this tutorial right now is being done in IPython, we are going to actually be using what's called the MB-AG backend, the notebook AG backend. Don't worry about what AG means. It's an anti-grain graphics library that we use to help make the figures look very, very pretty. So what we're going to do to activate the MB-AG, we're going to run this command, matplotlib.use MB-AG. And what MB-AG does, and this is a great feature that has been added in the 1.4 version of Matplotlib, is that it allows you to actually interact with the figures when it gets plotted up in the IPython notebook. Previously, you just simply get a static figure, and so you couldn't zoom in, you couldn't pan or anything like that. Now you can, which is a great feature, and we're really, really happy to have that. So, now that I got all that squared away, let's now talk about what we were here for, and that is plotting. So what is a plot? Well, the figure's still too big, Joe.
Yeah, sorry about that.
So a figure is this whole thing. And when you're plotting in Matplotlib and you get a figure window, that is your figure. And in your figure, you will have your axes, which is this whole thing. And your axes is made up of axes, Z's. So y-axis, x-axis. And so there's that hierarchy that you have a figure. Your figure can have one or more axes. Each axis can have 2 or 3 axis parts. And that's a very important hierarchy to keep in mind. And so this is the plot area, and that's the figure as a whole. Now remember, each figure you can have multiple axes, and obviously though, an axes can only be in on a single figure, so you can't have, and we've actually had people ask for this, like axes existing, like a single axis object existing in multiple figures. No. One axis to a figure, another axis to the same figure or another figure, things like that. Standard way of importing. As you guys probably have already learned, there's import NumPy as MP. And then the way to import Matplotlib is you don't import Matplotlib, you import matplotlib.pyplot as PLT. And you'll see this is a very, very common import convention. You could import it any way you want, but you'll see most code examples online and stuff following this convention. And so it's a good convention to follow. So let's get started and create a figure. Simple enough, fig equals plot.figure. Nothing happened. This is actually a feature, not a bug. Matplotlib will, by default, will not show you anything until you tell it to show it something. So all I did was just create a figure. I haven't actually told it to show. Those of you who are defectors from MATLAB will know the infuriation of having the plot, an incomplete plot show up, and then every single every single subsequent drawing command you give makes it go and have to re-render the whole thing while you're sitting there waiting, and all I did was just add a title. And so we don't show until you tell us to show. And indeed, now we're not showing much, but we got ourselves a figure. So while we're on this topic, you might have a need to control the size of your figure. And so one of the arguments to the figure function is the fig size. and it takes the specs a tuple of width and height in inches. Now, I'm not saying there can be that many inches on your screen, but if you were to save out the PNG file, whatever, going to know that, oh, it's so many inches wide, so many inches tall. And so then combined with the DPI, whatever the default DPI is, dots per inch, it will have the correct size for you. So we work in inches. But you might not really actually care about the exact inches in width, exact height and width, but you might care about the aspect size. So there's this function I absolutely love called fig aspect, and it returns that tuple in inches. But all you have to do is say what the aspect ratio is going to be. So I want it to be twice as tall as it is wide. I'll say plot.fig aspect 2. Twice as tall as it is wide. It will provide a proper tuple that will be of a reasonable size, and voila, it's really, really tall. I could do twice as wide as it is tall, and that will work. So nifty little function there I like. Now we're not here to do blank plots here, right? You actually want to start plotting things. So let's talk about the axes. All the plotting is done via the axes object. And as I mentioned, axes objects are made up of axis objects. So be careful whenever you say the plural of axis. We tend to say axes in order to distinguish between axes and axis. And so typically, when you get around to plotting, what you're going to do is you're going to create your figure, and then you're going to add a subplot. And a subplot is an axes object arranged in a grid. You can put axes object wherever you want, and we'll show some examples of that. But typically speaking, you want a grid. And so the easiest way to do that is to use these subplotting functions that will create that grid for you. So this is an older style of how we do subplots, and you'll see a lot of examples showing this. Fig.add subplot 111. Again, MATLAB defectors, rejoice. 111 is a MATLABism, and that means one row, one column, and give me the first one of that grid. And so you could do 1, 2, 1, 1, 2, 2, 1, 2, 2, 1 row, 2 column, give me the second one, things like that. So we support that MATLABism. John Hunter, who originally wrote the library, he defected from MATLAB 15 years ago, and so he brought along a lot of MATLABisms that he was familiar and comfortable with. All right, so really simple. And so we're setting ourselves some X limits and some Y limits, and we set ourselves a title, some labels, some X and Y labels, and then we did a show. By the way, in IPython, you don't actually have to do the show call, but in regular, whenever you're writing up scripts or you're doing it from a regular Python interface, you do need to do the show.
You do need to do the show in IPython the way we've set it up here. The only time
Yeah.
you won't need to do the show is if you use the Matplotlib magic command that tells about very start. So in most cases, you actually won't need to do show in the IPython.
Right.
All the ones here, because all the ones in this class are set up as do show.
Right. Yeah, that's an important distinction, right? I'm so used to doing the Matplotlib magic that, yeah. Because we did the use, it doesn't activate the magic, so, because we all know IPython is just magic. So, really, really simple. And so, just think about this here for a second. Just soak this in for a second. You just created yourself a plotting figure. Automatically, if you didn't have to tell it the ticks, so we have 0.5, 1, 1.5, 2. You didn't have to tell it that. Matplotlib did that for you. You set the limits, but if you didn't set the limits, it would have just done 0 to 1 by default, and it would have automatically decided what the ticks are going to be. So what I really love about Matplotlib is that it is it's really, really helpful without being stupidly obtrusive. It lets you I can easily override, what the ticks are going to be. I can easily override what the limits are going to be. So Matplotlib is not going to get in the way of me doing that, but if I don't tell it to do something, it has some really, really useful defaults. So it's not going to be stupidly unhelpful to you. By the way, anybody trying to scroll, if you're trying to scroll while your cursor is over the figure, it won't scroll. So you have to go off to the side. I think that probably should be a bug report somewhere. So one thing you'll notice with this style is that you'll have ax.set, xlim, ylim, title, things like that. So pretty much anything in Matplotlib will have these basic setter features, and you can set properties. And again, this may look familiar to the MATLAB users among us. So that's where it came from. And so you can really actually simplify out your code by having this all in one line if you want, for very simple property setting. But anything where you can do act.set for, or fig.set or anything like that, you can also do act.set underscore whatever it is you're setting. And that will, sometimes it's really nice for being explicit, but there's also other uses for that. So this is the same exact, this is basically the replacement of that act.set call right here. So it did pretty much the same thing. It's not going to show a figure because I didn't tell it to show a figure, but it will set those settings for me. And you go, oh, well, whoop-de-doo. If I have that set feature, why would I ever want this? Well, what if you want to set the font for one of these labels? That's an extra argument to setting the Y label. You can't do that in act.set because all you can do is just provide the first argument. So sometimes you will want set.y label, set underscore Y label, things like that, or set underscore table. So you can set the other arguments, so the font size, the color, things like that. Any extra arguments to a particular property, you'll need to do it this way. All right, enough of that. Let's now actually plot something. So there's two very simple plotting functions. One is plot, the other one's scatter. And so the main difference between plot and scatter is that plot will plot out a line, and scatter will plot out points without lines. And they can do some fairly similar things, but they do have some important differences. Funny story, one time way back when I was using plot, but then I realized I needed to switch over to use scatter, and so I just did a find and replace in my code for plot and changed it to scatter. Then I tried running the code, and it said it couldn't import matplotlib. Yeah. Yes, I'll be here all week, so don't forget to tip your waiter. All right, so we got ourselves an example. We're going to add a subplot, and we're going to plot out some data, really simple data, and we're going to color it light blue. We're going to have a line width of 3 points, and then we're going to do a scatter, some different data. We're going to give it a color, and we're going to specify a marker. We're going to go over some of these details in a later section. And so now you see the difference. You have yourself a line from the plot call, and you have yourself some points from the scatter call. And with the plot, you could do some markers. By default, it won't do markers. And with plot, you can also actually do it without lines and just do it with markers, things like that. There's all sorts of nifty tricks you can do with that. We'll go into more detail later about what you can do with it. So here you saw an example where we did ax.plot and ax.scatter. And you go, okay, you make the axes object do the plotting because that's the plotting you want in that axis. Okay, great, and you set the xlim for that ax, and everything makes perfect logical sense that this axis get those limits, this axis get that scatter call, things like that. You will often see, those are the axis methods, but there's also the PyPlot interface. And the PyPlot interface borrows a lot from MATLAB. In MATLAB, you don't have methods. You don't have an axes method where you did ax.plot. You just simply call plot. And those coming from MATLAB, you know that when you call plot, it does it for the GCA, the get current axes. It just automatically will do that. So we actually do have a similar sort of concept where we have the PyPlot interface. And if you do plot plt.plot or plt.scatter, plt.xlim, it will actually operate on whatever the current axis is. And the current axis is whatever is that has been last operated on. For those of you not coming from MATLAB and have no clue what the heck I'm talking about, don't worry too much about it. You use the PyPlot interface when you're doing simple things. When you got one or two axes and your script is really, really simple, you can, look at that. That's 4 lines of code to do exactly the same plot as the 6 lines of code above it. So you go, well, wouldn't I always want to do the PyPlot interface instead? Maybe, it depends. And my answer to that is that explicit is better than implicit. This is from PEP 20. PEP, for those of you not familiar with the PEPs, they're the Python enhancement proposals. They're kind of like RFCs, requests for change and stuff. PEP 20 is the 20 rules for writing good Python, of which only 19 were written. It's called the Zen of Python, and one of the rules is explicit is better than implicit. And so by explicitly stating that you want your ax.scatter, you're making it clear that the scatter plot is going here. Where if I said plot plt.scatter, there's some ambiguity there. What if you had multiple figures? What if you had multiple axes? Which one are you talking about? Programmatically, that can be confusing when your scripts start getting larger and larger, or let's say you're writing a little bit of library code for someone else to use. It may not be clear from your function which axes you're talking about. So all the examples you'll see, I'll be using the explicit interface. But this is also valid for quick and simple plotting. So we've shown how to do a single axis plot and you can have multiple plots in that axis. But how do let's say I want to compare something. I want to plot here and I want to plot here. Well, there is a function called subplots. Remember, there is add subplot, which is a singular, where you want to add a single subplot, where meanwhile, plt.subplots with an S will give you all of your subplots all at once in a NumPy array organized how it would appear. So I do plt.subplots, n rows equal 2, n cols equals 2. I will get a 2x2 array of axes, so axes object there, and I'll also at the same time get my figure object for it. So single command to get 2 things done at once. Remember before we created the figure, fig equals plt.figure. Now we're doing it all in one, so you can really simplify your code this way. And so let's see what that gives us. Beautiful. Wonderful. You get 4 areas to plot in. Wonderful. That's great. There's other arguments that you can supply to subplot, but right now we'll just work with that. So let's actually do something. You can see how, those of you probably have learned about NumPy arrays now, you can do indexing. So here, we're going to index 0, 0, index 0, 1, index 1, 0, 1, 1. So when it's a 2D array, so when you have, let's say, when you do arguments like this and you're saying 2 by 2, it will give you a 2D array. If I were to say one row, 2 columns, I'll get a 1D array by default. And if it's just 1 row, 1 column, I'll just get a scalar value, a single axis object by default. So it's a little special that way. The documentation really explains it well. You'll see examples. But let's see. So here I'm going to set the titles for each of them. And I'm going to also turn off the ticks so that way it doesn't get in the way of what I'm going to show. And indeed, I got my 4 subplots, upper left, upper right, lower right. So you can see, the 0, 0 was the upper left. So the first one, so we follow sort of how the image coordinates, if you're plotting images, the origin is up in the upper left corner. So 0, 0, 1, 1 is in the lower right. Okay, and then if you call fig.add subplot, if you call plot.subplots with no arguments, it will be as if you had done these 2 calls like this. So it can really simplify your code this way, if, just reducing it down to 1 line. All right, so you guys are probably getting bored of me talking. Let's create some plots as an exercise. So let's reproduce this figure. Now, what's important about this figure here? We have ourselves 3 plots. There are no ticks. We have ourselves 3 titles. And the data is a little bit different, in each one. So it's not exactly the same sine wave here. And right now, we'll even give you something to start with. Excuse me. And so we give you the data to start with, and we even give you the names. So now let's spend a couple minutes and try to produce a figure with 3 subplots titled that way with those sine waves put in, or cosines. We all know cosine is just a sine wave shifted, right? Okay. All right, so let's spend a couple minutes on that, and I'll take a little drink. Is there anybody really, really stuck still? Okay. We really gotta, wow, we lost. I was only hoping to spend 5 minutes on that. Okay. All right, so now we can close that out. If you guys want to save that result, right, we got to talk about what it is we did here. So what we did, we have, we have the data and stuff. We're going to create a subplot of 3 rows, very simple, and we're going to do a for loop, and we're going to zip over the axes, the data, and the list of titles, and we're going to ax.plot the plot, and then we're going to get rid of the text, so x tick equal empty list, y ticks equal empty list, but then also set the titles and the name, and then show, and that will produce our plot. Very simple.
Could you make it a little bigger up there? Could you make it a little bigger?
Make it a little bigger.
Yeah, just the text.
Oh, the text bigger?
Yeah, just the code.
Well, so then you could do, the text of the code?
I just can't read it.
Well, okay. For those who want to actually see, the solutions are actually already in your checkout of the repository. So you see that percent load above it, and I had exercises /1.1, whatever. You can change exercises to solutions, and then shift enter that, and that will give you the solution.
Probably it might be worth if we hide all the menu bars. If you go to,
How do you do?
I think in view there should be in that view of the of the notebook there should be a toggle header and toggle toolbar.
Oh, I did not know that. That is neat. I learned something new today. That's great.
Hey, Ben, would you mind terribly if I taught the second section? Just because I want to go over some specific things with the things, if that's all right. Because it's the one I added, or would you?
Yeah. So you want to do part 2?
Yeah, that's okay.
Okay. All right. So Joe will now take over in part 2.
Sorry for that. I didn't mean to. I just figured since one I added, there's some specific.
Yeah. Joe was very gracious to help me out. I just had my second child born about a month and a half ago. I did not have the time to revise this. Thank you. So Joe really graciously stepped up to help revise this this tutorial, and he basically rewrote this particular section. So I'll hand this one off to Joe.
All right, so thanks a bunch. So I'm Joe. I'm just going to go through this really quick. And what we've talked about so far is a lot of kind of what is a figure, what is an axis. We've talked a lot about Matplotlib in general, but you guys are probably here to make plots. So we haven't talked about the different plotting methods. We mentioned the gallery, and that's a great way to see a whole lot of different things, but it can be a bit overwhelming. There's a lot of functions on there. So this is kind of a condensed version of the gallery that just shows a few examples of the key plotting functions. And some of these we've already talked about, and a couple of these we're going to go over in a little bit more detail and work through some exercises on. The rest of these are just going to be a visual overview just to give you some sense of the things you're most likely to use. So you can come back to this and kind of look at it as a condensed version of hey, what are the 10 functions I'm going to use most often to make plots. There's a lot of more specialized things out there, but this is a good overview of a few of those. So one thing to mention, if you actually click on these, so if you actually click on these, it will take you to the code example that generated it. We're not going to go over that right now, but feel free to browse through that on your own time. Try to make those fairly readable, but it does go over some things we haven't talked about yet. What we're going to do is we're just going to step through these quickly and then do just a couple examples for individual functions. So we've already talked about plot. And what we kind of mentioned is that it plots lines. That's its main function. If you want to plot a line, use plot. What it can also do is we can control the style of that line. We're going to talk a lot about that in the next section. And then it can also plot markers. In fact, you can leave the line off, as Ben mentioned earlier. But that's basically what it does. Lines, markers. On the other hand, if you want to plot, oops, let me just.
2 fingers full.
There we go. All right, thanks. If you want to plot points, there's scatter. Scatter plot makes sense. The nice thing about scatter is it lets you control the size and color of the markers. So in addition to just putting them on there, if you want to scale them by 2 other variables, you can do that quite easily. So just to give you some sense, if you just call it with 3 variables, it's going to change the size of the marker. You call it with 4, you're going to get changes in color. Or you can specify that you want just color and not size change. So there's a lot of things you can do with that. We've talked a bit about scatter, so I'm not going to go over that in a lot of detail. Just know it's there. And then the other thing that we haven't talked about is bar. So as you might guess, bar makes bar plots. But really what bar does is it plots rectangles. So anytime you need to plot rectangles for some sort, don't think just vertical bars, think horizontal bars, or maybe you want to show time spans covered by different things. That's what bar is good for. There's also bar H, which is just bar with some different defaults. It allows you to essentially plot horizontal bars. That's why it has bar H there. Again, those of you coming from MATLAB background probably make sense. And then there's also fill and fill between. We're going to talk about bar and fill between in more detail. The reason is those are functions you'll use a lot. Now, fill by itself on the left-hand side over here, that basically makes a filled polygon. Honestly, it's probably not something you'll use a ton. What you'll use more often in most cases is actually going to be fill between. And the reason is fill between will fill between two curves or between a curve and 0. So if you want to make, or curve in any data value. So if you want to make a nice plot that shows something kind of more like this over on the right, but maybe just all the way down to 0, fill between is a great way to do that. The one on the right here is stack plot, which is just like fill between in several different things. So if you want to do, instead of fill between these two curves and then those two curves and the next two curves, stack plot's a way of saying fill between each of these successive curves. We won't go over that one a lot. We'll just kind of mention it's there. But fill between we'll come back to. Okay. And then we can look at 2D arrays and images. So we have a bunch of different data that focuses on, or methods that focus on 2D arrays. So if we have regularly sampled data and we want to color map it, we want to contour it, things like that, we have functions to do that. So IMShow is one of the most basic of these. It's basically for rectangularly, very regularly sampled data or images. If I just want to show a photograph, use IMShow. If you want to show data that's on a regular grid, use IMShow. pcolor and pcolor mesh will let you do similar things, except that they're less restricted. You can do arbitrary kind of grids. So they don't have to be rectangular grids. They can be these, other types. And then finally, you can contour things. So for those of you who are, I know we have at least one of the geologists in here, contours get used a lot in the earth sciences, probably a lot of other fields as well. But contours are very handy, so you can do that as well. Whoop. Yeah, I'm bad about that. A couple other mentions. If you have vector fields, so I work a lot with kind of flow data of various sorts, so it's handy to be able to plot up vector fields and show how things flow. There's a couple different ways you can do this. The simplest way, obviously, we can plot a single arrow, just want to mention that there. But Quiver is a good way to just show arrows on a regularly, well, it doesn't even have to be regularly sampled, just a lot of them. And then Streamplot will actually basically put tracers through there. So it's a convenient way to show kind of, imagine dropping dye into the water and seeing where it flows. And then the one last thing I want to mention is data distributions. Now, Matplotlib doesn't have as many statistical kind of specialized plots as, say, ggplot and R does, other things like that. There are packages like Seaborn, which is built on top of Matplotlib, that gives you a lot of very specialized statistical plotting capability. But we do have the basic things you'd expect. For example, if you want to make a quick histogram, if you want to do box plots, and we also have a fairly new, actually, I think it just came in 1.4, violin plot function. So these are all different ways of showing observed distributions of data. So just want to kind of mention those. There are a lot of other plotting methods in Matplotlib. You can go to the documentation, you can see a big list. If you just want to pull up, if we just go through here, actually didn't mention this earlier, so I'm just going to quickly show, for example, if I just do, there we go. If I just do AX, whoops. Take me a second here. What's tab complete not working there? Anyway. Oh, I haven't. And let me now. I guess tab complete doesn't work in notebooks. I thought it did. Anyway, if you were to do that, you'd see a whole lot of methods on there. I'm not going to go over that. If you want to look at them, there's a lot more there. All right, let's go ahead and talk a little bit about what we can do with some 1D series. So we're going to take and briefly cover bar plots. Obviously, a lot of people have seen bar plots, no big surprise there. One of the things that ax.bar, the basic thing we'll assume, is that you've got constant widths. So if we just take, notice what we're doing here. We're generating some random data. I'm going to make 2 columns of subplots, so it's going to be on basically side-by-side axes. And then we're going to put in a bar plot and then a bar H plot. It'll be the same data. So I'm just going to quickly do that really quick. What we'll see, and I'll explain the AXV line and AXH line in just a second. Maybe this is a little bit too big for the notebook there. Anyway, what we can see, this is ax.bar. And this is ax.barh. So we put in the same arguments to both of them, they just made some different assumptions. What happened with ax.bar is it assumed a constant width. So it took basically each one of these, it's 0.8 units is the default, but it kind of just spaced them through there. Bar h, on the other hand, assumed a constant height. So they both plotted rectangles, just made some slightly different assumptions. There's one other thing we did here, and I just want to mention this function really quick because it's very handy every time you want to put in a vertical or horizontal line all the way across. AXV line and AXH line. The reason they start with AX is they go all the way across the axes. So you're not plotting in what we'll call data coordinates. It will always span the entire axes. And AXV is for vertical, H is for horizontal. That part's pretty easy to remember. But anytime you want to put a line all the way across the axes, very handy way to do it. We'll also talk about moving the spines, but sometimes you just want a line there.
Do like a pan.
Yeah, yeah,
No matter
that's
how
a
much
good
you
idea
pan
here.
around,
It will always follow
go
that.
down a little
That's a
bit.
really good point. So yeah, and what Ben's saying here, notice no matter what we do, that line will stay at 0 in the Y direction and span the entire axis in the X direction.
What is the zero parameter, the first parameter?
So what that is, that tells it where we're going to place it in this case. Yeah, so it's where it should be. So if we put in 1, it would be at a data value of 1 on the Y-axis if it's AXH line, or 1 on the X-axis of the AXV line. So it sets it at a data value in one axis and then spans all of the other axes. It's a good question. Thanks for. Okay. One of the things that it's important to keep in mind is that all of the plotting methods return artists or sequence of artists or a container of some sort that has artists in it. Artists are anything you can see in Matplotlib. If you can see it in the plot, it's an artist. The figure itself is actually an artist. So artists can contain other artists. There's a hierarchy to them. But the key thing is we can hold on to it, we can modify it, we can reuse it. Use it for other things. So in this case, what we're going to do is we're going to take and plot the same thing, just the vertical bars, and then we're going to go through and modify those bars based on some of their properties. In this case, that XY is basically the lower left corner of the bar. So what we're saying is modify it based on its kind of the Y value of its lower left-hand corner. If that's less than 0, we're going to change its color. And let me just show you what this will look like. And notice we changed the ones who have that lower left corner less than 0 to red. Now we could have done this in a lot of other ways. We could have made 2 plot calls. We could have done a lot of other things to do this. But it's important to keep in mind we can hold on to those artists, change them, and it's very handy for things like animations. When we move on to the next section, we'll see how we're going to make color bars, and we have to hold on to it and do that. So let's go ahead. Now that we've talked about bar, let's talk about fill. So fill, actually we're talking about fill between, not so much fill. Let's kind of take the next thing. We can make a bar plot of the data. What we can also do is plot a curve and fill down underneath it. And that's what fill between does. So just to give you a quick idea of what that looks like, I'm just going to go ahead and run this. What we see, and let me walk through what we did up here. We generated some random data. Don't worry about the first few lines. Then we called fill between. If we just call it with just kind of XY data, it will fill down to 0 or up to 0. We can specify what that 0 is. By default, it's 0, but it could be 1 or 10 or 500. So if we were to put in the next value here, I believe it's just the next value anyway. Notice it filled up to 2. So we can change where that is. By default, it's 0, so I left it out and it just made it 0. But we can change that parameter. At any rate, it's going to fill between things. Between a constant value in this case. A lot of times that's not really what you want. What you really want is between 2 curves, kind of an envelope. And that's where fill between is particularly useful. So in this case, you may have an error envelope. You may have maybe observed kind of a min and max and then a mean value for each given time step. It's a great way to plot things like that. Okay, so in this case, what we have is an error envelope of some sort. I've just kind of made this up. We've plotted, with fill between, we've plotted that yellow part you're seeing. So what we've done is we've given it an X value, a Y1, and a Y2. And so it doesn't matter which one's top and bottom, it's going to fill between those two. It will matter which one's top and bottom, and I won't get into that. Anyway, you're going to fill between those 2 curves. So then we plot the black line on top. Pretty straightforward, and we get something that looks kind of like this. This is a handy technique anytime you have a range of values you want to illustrate. It's a good way to plot that up. Okay, so I'm kind of moving through this quickly. This is one of the more kind of tricky examples in some ways, but it uses things we've all covered immediately above it. So what we're going to do is try to reproduce this, and if you can come up with better labels for the axes, please let me know. I was making this late at night, and yeah, 100 somethings to whoever comes up with a better label for the axes. But anyway, just to give you some idea of the code you're going to start out with here. Oop. Come on. Oh, it did it down below. A little bit out of it. Most of this is generating data. Don't worry about that part. This is just generating the data we're going to plot. So all down through here, we've just basically generated a lot of data. Now we get down to where you're going to have to do it. Remember, you have to create the axes and figure. So first step with any of this is set up your axes and figure. You can look at this and see that's a single figure with a single axis. And then you're going to think about the plotting methods you're going to use to show that on there. All right, so let's go ahead and go through this, and please ask questions and go through things. Yeah?
Just kind of a side question. On the gallery and stuff, you have all the annotations and stuff on the plots. Do you do all that in Matplotlib? Or
Yes. So we won't go over those methods right away, but like, for example, in those first few, so all of those actually are, any text, you can put a box behind it. So any of the text methods, we'll talk about this a bit later. So there's ax.text, which adds text and data coordinates, pretty simple. ax.annotate's a little bit more complicated. You can do other things with it. We'll cover it in a later section. But it'll allow you to kind of place things in more arbitrary ways, and then also have arrows going to it. But really this, actually that guy up there, whoops, sorry, I should point with the mouse. That guy there is actually a function we didn't talk about called soup title. It's a way of putting a title across many plots. Again, these are the things that really a little bit outside the scope of this tutorial, but it doesn't matter if we just done that with title. ax.setTitle, you can actually tell it just put a box behind the title, and that's all that is actually. These guys down here, they aren't the X label, but if you wanted a box behind the X label, you can actually do that. You just, again, you tell it to put a box behind it. We'll go over a little bit of that later, not in a ton of detail. But if you're curious on how that works, if you click on the code example for this, it won't show it directly, but you'll notice it imports something called example utils. If you go to the, I just did that so they were all the same. I didn't have to put them in everywhere. So if you go into that example directory, it'll have that file called example utils. Take a look at that. It'll show you exactly what it's doing. But it's a really good question. But yeah, it absolutely can do it. All right, sorry, go ahead. Feel free to ask questions anytime. The documentation, if you're ever curious about what a given function looks like, I should have mentioned this before, but remember you can always, if you haven't used, if you put a question mark after the function and execute that cell, you'll get the documentation for that function. This is something I forgot to mention earlier. So in IPython, put a question mark after it, you'll get the doc string. That's basically a shortened version of the documentation. And so if you're ever sitting there trying to figure out what the heck something does, put a question mark after the function you're trying to call, run the cell, you'll get a little pop-up that'll go through the documentation. I meant to mention that when I was going over this, and I completely forgot. That was actually the main reason I wanted to go through it. I apologize. Completely forgot the main thing to mention. So if you're looking at it and trying to figure out what the heck am I doing here, notice that Y error. And then you can actually figure out some of the other things you might need from there. Won't worry about it too much, but that's basically what you were missing and what I forgot to say on the exercise. I don't want to rush you too much, but let's go ahead and walk through it a little bit. So, all right, first thing we're going to do is call up our figure and axes. All right, hopefully everybody remembered that part. That's one of the key things there. Okay, so we've got the axes. Now we want to plot our, let's say we plot the fill portion first. So in that case, we're going to do fill between, and we're going to put our x values. So one of the things you're doing here is a little bit hard to figure out is what you're filling between and what you're not. I probably should have gone over that a little bit clearer. In this case, you've got the kind of very top here. Notice you've got the x prediction, y max and y min prediction. That's what we're going to be filling between in this case. So we're going with the x pred, the x min pred, and you can actually put max or min in here first. That should be y. And then we want the color. And I believe I said the fill color there. So let's just do. Let me go ahead and show that. Oops, and Did I miss something obvious here?
Subplots.
Oh, yep, thanks. All right, so we've got the fill there. Now we need the bar. I'm going to close this guy.
Sometimes leftover from previous stuff.
Yeah. It's the, so bar, what we're going to plot are the X position. Yeah. I've apparently got this. Oh, 1 second. Let me just all output clear. All right. Okay, well, let me just load the solutions. I'll step through it. So I'm taking up too much time here. So what you'll see is basically we have the bar, the fill between, and plot. So we got 3 things we're putting in there. The first one's a fill between. You can actually do this in any order because the Z order will stay, they'll lay over each other in the same way. I plotted the fill between first in that case. Again, between the 2 curves and the fill color. The next thing is the bar, and these are these 2 averages. So basically the positions, the averages, and then the error bars. So that's the Y error equals that. And then notice I had a bar width up here. This was probably something that got a little bit confusing. So we had to put in a width, otherwise it'd just be a default value of 0.8. We want it to fill up a little bit bigger area. So we calculated that bar width up there. We need to use it. And then we have plot. So this is just putting that jaggedy line on top. All right, was that example probably a little bit confusing for people, I think? I probably didn't explain enough. Or do people generally?
It was okay with it. I just missed the fact that you had the bar left, so I was trying to figure out if there was a way to
Do the,
expand it or figure out what to do.
yeah, the bar width was actually a good thing I should have mentioned there. Yeah.
How did it know to put the fill between behind the bar?
Was it showed up in front?
No, I showed it behind, but I don't know how.
Oh, okay, so
I had the questions I wanted, I changed the order that I plotted them and it's still behind.
So, all right, the reason is that actually the order you plot them in doesn't.
You want to pinch the microphone?
So, oh, yeah. So that's a really good point. So if you wanted to move that bar in front, you notice you changed the order, it didn't matter, it still went behind. That's because, and we didn't mention this at all, we mentioned it in the later sections, the order they appear on the plot is controlled by another argument, and that's the Z order. So actually, if we were to do, I won't get into this too much, but if you do need to change the order something's in, that's where Z order comes in handy.
Is that always the case with like a stacked figure?
Yeah, so,
Since we're looking at the stacked area and like it, you know, normally like if I'm doing that in Excel or whatever, like I have to order my data so that everything is, you know, obviously, you know.
so, yeah, so it's always the case that Z order will control what they go into. In some cases, the order you call things in, if they're the same Z order, then the order you call them in matters. If they're different Z orders, then it doesn't matter, so if that makes sense. So the stacked figures, Z order will control what they do on a broad scale, and then if you have a bunch of them with the same Z order, then it does start to matter which order you plot them in. But that's basically this. So what I did here, to move that in front, I just put Z order really high. The bigger the number is, basically the later it'll be drawn. I think the default Z order for lines is 2.
Yeah, something like that.
Yeah, so it's kind of arbitrary. But if you're trying to figure that out,
We could find the default Z orders for anything and everything.
there's a page in the documentation somewhere.
Yeah, it's complicated. Just remember, you can always override the Z order. Always override it anytime by explicitly setting it.
That's the key. Is anytime you want to raise something up, change the Z order. And if you don't do that, it'll go in whatever the default Z order for the plotting method is. Okay, we are getting behind. I'm going to go ahead and move on to the next thing. Good, really good questions, so I really appreciate those. Yeah, no, thanks. But yeah, it's really good questions. I really appreciate that. So please keep asking those questions, even though we are running behind, because that's actually the most important thing. Okay, so let's go ahead and move on very quickly to images. I'm going to go over this pretty quickly. Images, we can plot RGB images, so that's For example, the one on the far right, we have a 3D array, or maybe, basically you have a 3D array, red, green, and blue alpha. You can plot that directly. But a lot of times you have just 2D data, you want to apply a color map to it. There are a lot of different functions that do that. We're going to talk about IMShow here. So IMShow, as I mentioned earlier, does things on a regular grid. pcolor and pcolor mesh do things on more arbitrary grids. So the key difference, I'm not going to talk a whole lot about the difference between IMShow and pcolor and all that. The key difference is regular grid and speed. IMShow can only show things on a regular grid, but it's really fast. So if you have a 10,000 by 10,000 array, IMShow is great. pcolor is going to get really slow. So that's the two reasons to have them.
There is actually one other very important distinction, and this is usually not an issue, but it can be in some cases, especially when you want very precise placement of your data.
That's true, yeah.
IMShow, the pixels refer to the center
Yeah.
of the coordinate. The center of the pixel refers to the coordinate, whereas in pcolor mesh and stuff,
the
the
edges.
coordinate refers to the upper left corner of the pixel. Okay, so it's a weird semantics, but some people love the pcolor thing, and some people love the IMShow thing, and it's like the it's like the Crips and the Bloods. It's just. I swear, I've had very, very heated arguments about this. So just know that there is a difference in terms of the exact placement. So
You can also actually control that too. You can make IMShow do exactly what pcolor does. It's just a lot of different,
by manually shifting things.
Yeah. So, but yeah, that's a really good point. IMShow's center aligned, cell aligned, if you're used to the kind of the GIS terms. So one's cell aligned, one's mesh aligned. Yeah, it's actually a really good point. All right, so what we haven't talked about though is color bars. So if we're displaying data, z-values, based on a color map, we probably want a color bar. All right, so let me go ahead and just run this example so you can see what we get. What I've done is I've loaded in some data. Now this is example data, but let me just actually do that. Okay. So notice the data is a 2D array. It's a big 2D array. We don't have to worry too much about it. But it's just a 2D array of z-values. And then we've set up the figure. We've called IMShow of just the data. And we actually did specify a color map here. That's the CMap argument. We'll talk about that more in a second. That's the color map. And then we made a color bar. Now I'm going to talk about those in a second. What we get is this. Here's our data values mapped to a color bar. And then we have a nice color bar beside it. If we had just called, let me go ahead and clear this output. Current output clear. If we had left that out, we wouldn't get the color bar. So fig.colorbar will show the color bar. All right, so you may be wondering why we called figure.colorbar. So we called fig.colorbar and not ax.colorbar. The reason is that fig.colorbar adds a new axis, and therefore it's a figure method. So axes methods, remember they plot on an axis. So you're calling that axis's method to plot on it. With a color bar, it actually doesn't go on that axis. It actually goes on a new axis, or you can control which axis it goes on. Therefore, it's a figure method. So it doesn't operate on the axis, so it goes on a figure. For that reason, we actually need to pass in which thing we're going to basically show the color bar for. So you notice what we did in all these cases, we've hung on to the image object, the image artist that IMShow created, then we've used it to make the color bar. So we've said exactly which artist this is for. You could have 20 different things, but you need to say which one you're making the color bar for. Okay, that's the basic idea. If we want to get more fancy, if we don't like where that goes, you can actually control exactly where this color bar goes. We didn't really mention add axes earlier, but that's the most low-level way to add an axis. What this does is it lets you control exactly where it goes. I'm not going to show the documentation on this. You can look it up, but basically that's a left, that's a Y, basically a bottom, that's a width, that's a height. What we get in this case, we're saying make a new axis that actually overlaps with our old axes, and then put the color bar in that. That's that CAX argument. I'm not going to talk about this a whole lot, just want to mention it. Basically, you can do crazy stuff and put it, not crazy, but you can do things like insets. The key is you need to actually make the axes on your own. So there's not an automated way to make an inset axis. You have to place it yourself. There are, however, automated ways to do some other nice alignment things. And just as a quick plug for the last module, we'll kind of mention Axis Grid, which lets you line things up automatically, do some more fancy things with these. Okay. One of the key points with IMShow, pcolor mesh, actually even scatter, they're all what's called scalar mappables. All that means is you can show a color bar for them. It means they map some range of data onto a color. But the key is they're going to have a lot of keyword arguments that are the same. So a lot of these parameters are shared between them. One of those is CMap. We're going to go over all the different color bars in a bit, but CMap is the argument that lets you control the color bar. Notice that showed GIST Earth. That's the name of a color map. There are also a bunch of others, but you can say which color map you want to use. Vmin and Vmax. This is something that gets asked a lot, that a lot of people I think look for and don't find quickly. If you have a range of data and you want the color bar to always start at say 0 and 1, but your data goes from 0.05 to 0.98, by default it's going to map it to 0.05 to 0.98, and you really want that to be 0 to 1. Vmin and Vmax change that. So Vmin and Vmax are ways to say exactly which values the color bar should stretch over. Does that make sense to everybody? Basically, it's just setting the lower and upper bounds of that color bar. And so the colors that are displayed will stretch according to that. A lot of times, this is really useful when you have something. For example, I'm going to take that same data. I'm going to use a color map called seismic. It just means it has white in the middle, red and blue on either end. Let's display this. And you kind of see what I mean here. All right, so what we have this data. We have a color bar. Really what this is, these are anomalies from 0. And notice 0 is this pinkish value. And we really kind of like it probably to be white so we can show these anomalies correctly. A quick way to do that, there are other ways, but a really quick way to do that is just to specify the Vmin and Vmax. These range from about 2 to -2. So we can put Vmin equals -2, Vmax equals 2. And what we get is a symmetric color bar about 0. Notice now, the color bar goes from exactly 2 to exactly -2, and 0 is in the middle. Does that make sense to everybody for the most part? Okay, we are probably running pretty short on time. You want me to just walk through the last example instead of, all right. One place this is really handy, and I encourage you to kind of walk along with this. We're probably talking too much, and the examples would be good to go through, but, or I'm talking too much.
You want to close that dock string.
Yeah, thanks.
It's off to the side, it's off to the right hand side.
I'm missing the, I can just click to, come on. There we go. Yeah, thanks for that. Okay, so what we have here, we want to have 3 different images share the same color bar. All right, this is a common question that comes up a lot. I have all these different images. I want them to have the same color bar. How do I do it? The key is you set them all to have the same range of Vmin and Vmax, and then you show one color bar for any of them because the color bar is actually the same. So that's the trick. You use Vmin and you use Vmax, and you show them all. So in this case, I'm going to go ahead and walk through this. We have the 3 figures. Actually, I'll just go ahead and pull up the solution. This one actually is a very quick. So 3 figures here. I set all this up beforehand, so I already laid these out and generated the color bar axes. Now, this part, it was already there for you, but again, this is manually setting up the axes for the color bar. You can do it in other ways. I didn't want to dwell on that too much, but it's one that was kind of long and narrow and centered. So basically that sets it starting at 0.25 away along 0.1. These are in actually percentages of the figure high. That was already there. I'm not going to go over it too much, but the key thing, we go through, we set up our data. We have these 3 data sets. We plot them all with the same Vmin and the same Vmax. Now, I didn't mention this too much earlier because I was trying to go through it quickly, but interpolation we can turn on or turn off. In this case, we're going to turn off the interpolation. We're going to say nearest interpolation. That effectively turns it off. And what we do then is get the cells basically as nice little squares with no interpolation in between. And the Vmin and Vmax there, notice we've got them set. We can then display a color bar. It doesn't matter which. This would actually return 3 separate image axes objects. So 3 separate images here would be IM. So the first time it goes through the loop, it's one. Second time, it's next one. Second time, it's another. Since they have the same Vmin and Vmax, it doesn't matter which one we display. So when we call fig.colorbar, we can use any of them. We just need to specify that CAX. That's this new axis down at the bottom. An orientation equals horizontal. It's pretty easy to figure out what that means. It just means draw it so that the colors range horizontally and not vertically.
You know, to get the tick.
Yeah, and you get the
And
ticks
then
horizontal.
label for it.
So if you hadn't put that in, you'll get a very, as you take that out, it'll still be in the same shape, but it's going to look really weird. So if you ever get something like that happening, that's the orientation part. Okay. I worked that on, I didn't have you guys do it, and I apologize for that, but hopefully that made some sense. A lot of those examples in particular are made so you kind of left some things to figure out as you went, which means the examples took a bit longer, so I'm probably running way over on time. But any questions before we move on? Hopefully there are questions. Please feel free to ask questions.
Anybody need a moment to go grab coffee or something like that? Now would be a good time before we power through the next few sections. We're short pressed for time right now, so we're going to get moving. Part 3. How to speak MPL. In the previous section, you've learned how Matplotlib organizes plots making by figures and axes. We broke down the components of the basic figure and learned how to create them. You also learned how to add one or more axes to a figure and how to tie them all together. You even learned how to change some of the basic appearances of the axes. Finally, we went over some of the many plotting methods that Matplotlib has to draw on those axes. With all that knowledge, you should all be off making great and wonderful figures. Why are you all still here? Nobody wants to read the next line? Nobody wants to read the next line? Thank you, exactly. You know, the first time I gave the presentation, someone did that totally unprompted, and I was just,
That person didn't show up today.
I should pay someone next time. Of course. The previous sections have taught you some of the structure and the syntax of Matplotlib, but it did not talk about the substance of it. It hadn't talked about the vocabulary of Matplotlib. It hadn't talked about the properties and how to set them and things like that. This is the language of Matplotlib. So we're going to start off with colors. There are many different ways to specify colors in Matplotlib. Most basically, it's just a string of either the letters B, G, R, C, M, Y, K, and W, or their names themselves, blue, green, red, cyan, magenta, yellow, black, and white. So you can specify the string of those wherever you need to specify color. Or one of the other, there's also a full list of 147 color names that we support. They're all from the CSS HTML specification. So we have the full list there. So if you want Burleywood or chartreuse or whatever, I have no idea how to pronounce that. I'm like Windows 3.1. There's 16 colors. And then for the British-speaking people among you, we accept both forms of gray, G-R-E-Y and G-R-A-Y. So anytime you need to say light gray, dark gray, things like that, we accept both spellings. So very useful there. For those who are used to doing things in hex, where you got that hashtag and then the 6 letters and numbers after it, we accept those as well as a string. If you want to specify a shade of gray, now this joke was actually a lot funnier like 2 years ago, 256 shades of gray. So you can specify as a string representing the numerical float value. So quote 0.5 end quote. that would then be interpreted as a halfway gray color, a halfway gray. So you have 0.0, that would be black, while a quote 1.0 quote, that would be treated as white. Anything that can be interpreted as a float number, that will be, but is a string. So if you gave it 0.75 as a float number, it will not interpret that as a gray thing. As a matter of fact, it will just yell at you and say, what are you doing? So you give it as a string and it will do that. Then there is the RGBA tuples. Very rarely will you have to actually do this, but if you get down into some of the lower level parts of the Matplotlib API, that may be all that it accepts. It may not accept the color names and stuff. So if you do a tuple of the red, green, and blue channel, and then sometimes the alpha channel, which is the transparency, you do one of those tuples or a list of those tuples, that will also work. So let's play around with this a little bit. We're not going to go off and we're just going to literally do this right now. So I have set up here a simple plotting function, and let's just do some colors. So I'm going to do cyan for the linear plot, and then for this one, let's do burly wood. And then let's do for that cubic curve, let's do 0.75. And very, very faint here, but you can see you got 3 different colors. So you can control that. Next, we're going to move on to the marker. So you saw that plot there. There's no markers indicating the points that we're plotting. It's just simply the lines. So you can also specify the markers. And there's a whole list of markers that you can do. Things that are in quotes are things that are expected to be strings. Things that are not in quotes are not expected to be strings. There are some places in the code where you can't do, let's say, the numerical values. So the tick left, tick right, caret up, things like that. Those are all numerical. You can't pass those into plot, for example, or scatter, but they're used elsewhere. You can have a string value of none. You can have the actual object none. You can do an empty string or a string with just a space in it. They also are nothing. So if, let's say, you're doing a plot that would do a that would put in markers and you don't want it to do a marker, that's how you can tell it not to do that. So let's actually take a look at what those markers all look like. That's what the next code block is for. That's what they look like. Quite simple. That's what they do. So let's, now with plot, getting into some of the details with plot. Plot, you saw me do the strings earlier where I did cyan. Well, if you do the individual letter, you can also specify the marker. So I can have a star. I do star then color, right? Or is it color then star?
I actually think it'll do either in most cases, but usually it's the color and the marker.
Right. See, star. I think you could do that, right? I always get myself a little confused here, but let's just right now just focus on just the marker. So let's do star. We could do big diamond and do what's another marker we can do? We can do let's do an octagon. So that would be the string value 8. So now, you see you got a plot. And also notice that the line went away. We'll get to that in a second. When I specify just a marker, you're basically also telling it, hey, don't do a line, because I didn't specify what the line style should be. So if I wanted the lines to come back, we'll get to that in the next section. You'll see how to do that, but you see you got the different markers. We got the star, we got the diamond, and we got ourselves an octagon. Now we move on to line styles. There's a few preset line styles. There's the basic solid line, that's just a hyphen. Dash is 2 hyphens. Dash dot is a hyphen, then a dot. Not a dot, then a hyphen. Because if you do a dot, then a hyphen, a dot is remember, well, probably don't remember because we just went over it very quickly, but a dot, being just a period, is one of the, trying to scroll here, is one of the markers. So if you do a dot and then a dash, it thinks that you want the dot marker with a solid line. So if you want a dash and dot, hyphen then period, and then if you want nothing, you can say in quote none, or just a space or an empty string. So back in the previous example where I just specified markers, it thought that I didn't want any line style because that would be an empty string because that was all that was left. So, and then dotted is colon. And then you can actually also specify custom line styles where you can specify the amount, how long, you could, it's called the inking. That's more complicated. There's documentation on that. I'm not going to get into that right now. But so we have an example here where we have a dash. So that's a solid line. We have dash dash. That's dashed line. We have a dash dot for the cube, and then we also have a colon just to kind of show that example. And there you go. We got ourselves 4 lines. Note that the color for each of these lines change. Is a different color for each of these lines, but I didn't specify color. In Matplotlib, some of the plotting functions will cycle through a color cycle. This is another MATLABism. So if you're doing bar plots, each call to bar, each call to or hist or scatter, plot, some of the functions like that, each subsequent call will do, if you don't specify the color, it will specify it will go ahead and cycle through colors for you. So in this case, we didn't specify colors, therefore it came up with them itself. Okay. There's also the names of those draw styles: solid, dash, dash dot, dotted. There's some places in the code in which it will not accept this specification, the shorthand. It would expect you to say the name. So for example, bar plots, it wants the name dashed. You can't do dash, or you can't do hyphen hyphen. That should be fixed in the next release of Matplotlib. I believe that, well, not the next release, it will be the one after the Colormap overhaul that I'll talk about soon. So then you can specify either the shorthand or the name any place that specs a line style. So Okay, so we talked about line styles, we talked about markers, we talked about color. So those are the three most common properties that one typically will be messing around with that involves an actual language. So you can also mess around with the size of the markers. So marker size equals whatever number you want in points. You can specify a few other things. So what are those other properties? So there's alpha, there's obviously the color. For lines, you can specify how it's going to cap at any time it makes a corner. It'll specify that. How it joins when it joins up at different segments. So bevels or round or miter, things like that. There are people who really care about this. It's also really important when you have dashes so that when it does corners that it still shows the dash for the corner, that it's not happen to be a spot where there's a gap in the dashes. So that's important for many people. There's draw styles that's a little bit complicated. It more refers to exactly where it's going to, does any turns happen at the coordinate? Does it happen in between the coordinates? It's a little complicated, but that's there. Line styles, line width, again in points, the marker edge color, or for short MEC, marker edge width, or MEW, marker face color. So the marker has edges, and then there's also the face of the marker, so you can specify colors for each of those. Or if you just simply say what the color of the marker is going to be, that will be for both. Marker size, cap style, joint style for solid lines, so you can specify how those things are going to be for whether you're doing dash or solid. Whether or not it's going to be visible. This is a neat thing that you can do sometimes, especially for interactive applications using Matplotlib. book. You can turn artists, so you can plot everything up you want, but then you can manually set individual elements to be invisible for a moment if you want. Make them disappear. This is also useful for animations and things like that, so you can turn visibility on and off for different things. And then, as Joe mentioned in the previous section, the Z order. So many objects have a default Z order for layering. That's how Matplotlib works. Matplotlib has a layering engine, so as artists come in, it will sort all the artists up by their Z order and then plot them in order, and it's a stable sort, so anything that has the same Z order, based on the order that you have created them, that's the order that it will get displayed at. So that's how you can control overlaying. So objects, there are various types of objects that you have default values that make sense for 90% of the situations that you might come into. So, for example, bar plots has a lower Z order than line plots, because you typically want lines on top of bars. So we have default Z orders, but you can always override the Z order if you want. All right, we're going to walk through this exercise. So we're going to make a plot that has a dotted red line with large yellow diamond markers, and those diamond markers have green edges. So, so we're going to say we want it to be a red line. Let's just see what that looks like. That's what I love about IPython notebooks, is that you can, just build up your plot little by little. You don't have to do it all at once. So, okay, I got myself a red line. Now I need yellow diamonds. So I'm going to say marker equals capital D for diamond, a large diamond. If you do a lowercase d, that's a small diamond. And marker face color equals yellow for or Y, and marker, well, let's just see what that looks like. Ah, yep. So now you see you got yourself markers, but they got this stupid, I don't know if it's blue or black outline. You don't want that. For some reason, you're really crazy and you want green. Marker edge color, or I can say MEC equals green. There you go. Now your diamonds have green outlines. And that's how you do that. So you can combine all these different other arguments together to make it. I probably actually could have said, I wonder if I just simply had done this. Yep, still work. So you could do color of the line, and then say that it's a diamond, and then I can say that the marker face color, or the MFC, is yellow, and the MEC, the marker edge color, is green. So that makes sense, everybody? Now you're speaking the language of Matplotlib. You're able to customize your plots. You're able to tell it to do whatever you want it to do, all through these other arguments. Not saying that you should argue with your computer, but you can. Color maps. This is so insanely important, but yet so many people skip over this thing. So first, just to say, all color maps do is they assign a color for a value between 0 and 1. And then you also can assign a color for anything anything below 0, anything above 1, and then anything that is invalid. So nans, for example. I have a problem with power. There we go. So that way you can plot just about anything you want and be able to control your plots any way you need to. And so you go, well, wait a minute. Your color map only go from 0 to 1, but my data goes from -50 to 75. With the color maps, we also have what's called the normalized objects as well. And so that normalized thing actually, you typically never play with it directly, but it's the one that will normalize your data so that it knows things that are 0. It will represent your data as 0 to 1, or things that are below 0, things that are above 0, or things that are invalid. So you can actually do some really, really neat stuff with that. So if you have categorical data, so let's say you're doing Landsat images and land use images, you can actually have a norm object that converts the categories to a color, and then anything that's outside of that category gets some default color or gets nothing or things like that. So it's really, really useful for things like that. So that's color maps and normal object. Now the default color map in Matplotlib is Jet. And it's a really, really colorful color map. It can be really good for visualizing differences and things like that. And it goes through the entire spectrum. But it's horrible in terms of for helping people with color blindness. It's also have been found to actually cause medical errors when people trying to interpret medical images. There have actually been documented cases of medical errors made because they could not visualization using Jet color map actually caused misinterpretations of the data that they were seeing. MATLAB in the latest version has changed their default color map and to something called Perula. It actually looks fairly nice. However, Matplotlib, we are right now as a community working on coming up with a new color map. Right now, this map here, up here, is the leading contender. We haven't come up with a name for it yet. So if anyone can come up with a name for this color map, that would be awesome. Right now, I'm just calling it option D. You know, kind of like Chanel number 5 or, you know, Heinz 57. So if anyone can come up with a neat name for that, that would be really neat.
I would call it Starry Night. It looks like Van Gogh's color.
Send an email to the mailing list.
Lukewarm.
Oh, yes, because that's a real power name right there, yes.
Can we get it now, or can we get it? Does it have any number or name?
It has not been added yet officially because we're trying to decide on the name. And we're also, there's some people that tweaking this a little bit to try to make it just a little bit better. But there's been a bunch of options. There's actually a few other color maps that have been working on, but I'm not going to get into that right now because that's a separate thing. But do recognize that actually probably during some of the sessions this week, we're actually going to be having some debates and discussions, maybe some fisticuffs, not quite sure, with regard to these things. So please come and give your insights to color maps because we really want to pick one that works well for many, many people. So to show you kind of what is right now available in Matplotlib, give this thing a moment to run. There we go. It's going to generate a whole bunch of figures of the many, many different color maps that are available. By the way, you see all these names. So let's say greens. You can do an _R and it automatically reverses it. So any of the standard names. So if you were to make up your own, it doesn't automatically reverse that. But for any of these, if you do an _R in the name, you'll get the reverse version of that. So these are sequential color maps. They're good for certain types of data. These are some other sequential ones. Then you have diverging ones. That was sort of what Joe was showing earlier, where you have negative and positive values that you want to center at a particular place. Qualitative color maps. So that's typically used for categorical data. And then there's a few other miscellaneous ones. I've never understood. MATLAB has flag, which is just red, white, and blue over and over and over again. I've never understood that one, but it's there, so.
I have actually used it. Really?
You have?
It was for big data, but I wanted to show what INSAR looked like.
All right. So how do you call these things? Well, you just CMap equals and then the name of it. So let's just take a look at a couple plots. Same data, but using two different color maps, like so. All right. Any questions about color maps? Because that's just so insanely important. It's just... All right.
Is there a list of them available?
I'm sorry, what?
Is there a list available?
Yeah, oh, yeah. I think I included a link in some of the text up there, that wall of text up there. I'm pretty sure
All right, thanks.
no, I did not include a link. But on the Matplotlib webpage, there is actually documentation. If you do choosing color maps, choosing color, yeah. There's actually a whole explainer talking about the different about why one would choose one color map over another and things like that. And also why some color maps are just absolutely terrible. So it's a really, really good lesson if you ever want to learn about how humans interpret color. It's really fascinating. So, all right, back to the tutorial, because we got to hurry up. Ha! Okay, so I'm assuming most of us here are all scientists. How many people here deal with LaTeX? Right. So you're probably looking at some of those labels and going, ugly, terrible. It doesn't look nice at all. And then how would I do the Greek letters and things like that? Matplotlib, don't worry. Matplotlib supports what we call MathText. And basically it's sort of it sort of looks like, it emulates LaTeX in some respects, in particular the MathText type stuff. So if you were to do $ and then \sigma _ I = 15 and then $, I mean, that looked like LaTeX to you, right? Something you all love and know. You can do that. Note that in Python, when you make a string and you have a \, to it, if let's say you're doing \new, well, you have a \n, so it's going to interpret that as a carriage return. So if you do an R before the string, it will treat it as a raw string, and therefore it won't treat the \s as special. So you do that. It's also really useful if you're doing regexes, regular expressions, because there's a lot of \s and regular expressions as well. Yeah. Although if you're doing directories and Windows and stuff, you should be using os.path. So and os.
You also accept // on Windows incidentally. Python will happily.
Yeah, it does.
You can use // too.
Yeah.
It is very handy for programs.
But notice, look, I got myself a sigma up here with an I, and then = 15. Oh, right, yeah, because I didn't do curly braces. Sorry, it's been a little while since I've done curly brace. There we go. Sorry, my LaTeX skills are getting a little rusty, but yeah. So you got the I = 15. If, you know, just demonstrate. So anywhere where you can specify text, you can do MathText. Anywhere. So it will do that appropriately. Now it doesn't, and you don't even need LaTeX installed on your computer. It will do the really basic MathText on its own automatically for you. But you can delegate out to LaTeX if you want to do more complicated things, but I'm not going to cover that here. But that is also possible. Annotations and arrows. So you want to anytime you want to, you can plot arbitrary text and put it anywhere you want, and that's plt.text. But you can also annotate things, which is the text with an arrow pointing to whatever you want. So let's say I have this plot of cosine. I want to point out the local max of some data. I can say annotate, and the text of that annotation will be local max. The location of the arrow will be at the data point 2, 1. The text will be at data point 3, 1.5. And then if I want to specify some properties of the arrows, I can, but I don't have to. And now let's plot that. There I go. I just pointed out the local max with an arrow. Note I called plot.ylim and specified that the y limits are -2 to 2. There's a reason for that. If I didn't do that, that annotation will just float off out here because it's no longer, because remember, there's auto-scaling and it's going to, I don't think we covered auto-scaling yet. It will it'll cover the limits for the data. Meanwhile, the annotation is not data, so it doesn't take that into account. So there's that. Question? All right. And then you can do all sorts of things. You can put boxes around that. You can do special kinds of arrows and things like that. So I'm going to show the different kinds of arrows here. Don't worry too much about the code. Just see that these are the different kinds of arrows that you can do. And then there's some people working on coming up with new kinds of arrows. So if you just simply want a line, you can curve them. You can do all sorts of things. So you have a full range of options for your arrows. You get any arrow that you wish to have. So, and then, like I said, there's some people working on creating some more kinds of arrows so that we can have even fancier stuff if we want. So, I'm not, again, we're really pressed for time, so I'm going to skip this exercise. Just remember, this is just an exercise playing around with annotations and stuff. You can always get the solution by changing that exercises over to solutions. This is how you cheat. And so basically, it was just changing that previous example to point out the local minimum with a red arrow that is fancy, things like that. I have a mistake here.
You need to be shrink B. Does it shrink?
Oh, yeah, the shrink thing. Yeah, that was a bug that got fixed recently, isn't it? Now, see, I just did a different kind of arrow, and I pointed out the local min, so it was just changing that example. All right. Hatches. So we talked about markers, we talked about colors, we talked about line style. There's also hatches. Personally, I use hatches for situations where, let's say I'm already using color to indicate something, but I got some other piece of information that I also want to indicate. I can hatch my polygons and such so that that's a second dimension of data that's on top. The other thing that's really useful for hatches are for those who are doing publications in black and white publications, so you can't do color, or just to be colorblind friendly, you can have different hatches for your polygons, so that way it can be very visually distinctive. So there's a few different ways to do it. You do // backslash, vertical bar, dash, plus sign for cross, X, a lowercase 0, a lowercase o, uppercase O. You could do a period for dots. You could do asterisk for stars. And then one thing that's neat is that if you repeat a symbol, it would increase the density of that particular hatch. So let's do an ugly tie contest. You understand in a moment why I do that. So I got myself 4 bars that are going to be shown here, and I'm going to hatch them differently. The first one is just going to have X. The second one is going to have a higher density of X's with dashes. I'm going to have the third one going to have pluses and O's, and then the last one is going to have stars. Because my God, it's full of stars. I don't even get a chuckle for that. I know. Stick with my day job. I know. Just ugly tie contest. So yeah, you could play around with that, and you can. So you see how Doubling up the x's, increase the density of the x's, having the stars there. Apparently the way you can make them bigger, but I can't remember off the top of my head how to do that, but that's how you do hatches. All right? Last thing, I'm not going to get too far into this, but it's important to understand the terminology. Matplotlib, the reason why Matplotlib does so well is that it has what's known as the transform system. You may have been noticing that some things you specify in points, some things you specify in data coordinates. So like when we did the annotations, we specified that the arrow was going to point at 2, 1 in data coordinates. That the XY text was going to be at this place in data coordinate. Meanwhile, when we did the add axes, probably didn't say it explicitly, but those were all in figure coordinates. So fractions of the figure. So this wide and going to be half the width of the figure, or going to be located here. So, but we never specified which coordinate system these things are going to be in. That's because the different functions will assume a different part of the transform stack. And the transform stack is that you have things in data coordinates, you have things in axes coordinates, and then, so data location, so when I say that this point is going to be at this location in data, that's where that is. But then I can also say that it needs to be at this location in the axis. So it has to be halfway through the y-axis. I can say that if I wanted to. And then, but those subplots, they're all inside the figure coordinate system. But when you specify the location of a point at data coordinates, you didn't have to know anything at all about where it sits in the figure coordinates. Matplotlib takes care of that for you. You don't even realize it's happening under the hood. But it has to transform all those data coordinates to, finally, the screen coordinates when you display. So you have data, axes, figure, screen. And so Matplotlib, under the hood, has this transform stack so that it knows where all the coordinates are in the stack and will finally transform everything all the way up to the screen coordinates so that you get your data plotted exactly where you want them.
One quick note, just to plug Ben's book for him. This actually really starts to matter mostly when you make interactive stuff. So it may seem kind of arbitrary making a static figure, but when you start panning and zooming and resizing the figure, this stuff really matters, and it's how it's all handled. So as soon as you start making something that you want to have a little application that, you're going to, someone may resize the figure, someone's going to pan, zoom, all that, you really start worrying about this. So just so you know, again, Ben's book, but that's where you worry about this.
It's really advanced stuff, so that's why we don't have an example displaying and stuff, but know that it's there so that when it comes time, it's there for you. There's an entire tutorial about it that's really advanced. You can do that. So now you're thinking, wait, so we learned all this language of Matplotlib and all this syntax and vocabulary and stuff, and you go, do I really need to specify all these things all the time? The answer is not really. Some places you still do need to specify things by explicitly, but in other places you can actually change the default values of these things, and that's Matplotlib RC. And Matplotlib right now is transitioning over towards a style sheet approach of things, so you can actually create styles or use some of the default styles that are built in and really try to customize your plots so that way all you have to say is, I want this style, and you don't have to actually specify any of the other arguments, and it will plot things the way you want to. So just kind of show how that's used. We're going to change the style, the default style of lines to be line width of 2 and to be dash dot. So we see that So for the first plot, it came up as solid because that was the default, but then we changed the style and now it's like that. So it's the same exact calls, the plot. So ax2.plot, same exact call as it was for ax1.plot, but because we changed the style, the RC, then we were able to customize the look and feel. And so there's a whole bunch of things that you can customize in your RC file. Won't go too much into that. You can find your RC file by running these two commands up here. So you can modify that to your heart's content. And then, like I said, we're working on a style system so that you can actually pull in a bunch of different default styles. So there's some people that are working on coming up with styles that work well for different kinds of publications. So that way your plots look like what it should look like for a particular publication. So that way you can make one script, generate your plots, but let's say your publication wants things, your fonts have to be this, or your font sizes have to be this and stuff, and that's not what you want for your normal plotting. All you have to do is do the same exact plotting, but with a different style. You can run your script again without having to change your script with that new style. So that's that. That's part 3. Other page. Okay. Now on to part 4. Because we have so much time. Okay. So, we're going to power through this. Now we're going to talk about the 3 L's. Limits, legends, and layouts. First things first. Again, when I talked earlier about Matplotlib, it cedes you as much control as you want, but without being stupidly unhelpful. So if you don't say what the limits are going to be for your plots, it'll try to figure it out for you automatically. But you can always override that. So it will try. So that's called the auto-scaling feature. And so we're going to take a look at an example. We're going to create 2 subplots. They're going to both plot the same data, but one's going to use plot and one's going to use scatter. And you're going to notice a subtle difference. So with plot, the limits are very, very tight so that it all touches the edges of the limits of your data. But it also tries to pick integer values for the data. So notice it didn't just stop at 3.5. It went all the way up to 4 because it looks nicer that way. So that's one of the things I really like about Matplotlib is that it picks ticks and limits that make sense. Now, if you go over here to scatter, you notice a slight difference in the limits. So here, the x limits was -10 to 15, whereas for scatter, it's -15 to 20 is a little wider. For scatter, the assumption is that you actually want some sort of margin for your scatter points, and so that it will automatically pad the limits a bit so that it will, limits of your data so that way, because if you have a point that's right at the edge of your plot, you may or may not notice it. And so we like to pad that just a bit. We pad by 5%, 10%, something like that. So that's what's useful there. And that's what's done automatically. Now, you can actually change the amount of padding. So for basically the idea is that with plot, you get no padding, but with scatter, you get padding. We can change how much padding we get with ax.margins. So again, we're doing the same exact plot, but now we're going to do a margin of 0 in the x direction, but 10% in the y direction for the plot, and then we're going to do 5% margins all around for the scatter. And we see that the limits are now a little bit different. So now you got a little bit of space down here, but it's still nice and tight in the x direction. But now the scatter plot's a little bit tighter for its limits. So very, very useful. So if you want to know what the limits are going to be, there's a few ways that you can do that. One, to get all four x and y limits, you can call ax.axis with no arguments, and you get all 4 of them back. You can also use ax.axis and say what the 4 limits are going to be. But typically you don't do that. Typically you'll call set y-lim, set x-lim. What you typically will use ax.axis for is saying whether or not it's going to be tight, so that basically no margins, or to say if it's going to be square. And that is, and the idea with square, we'll show here, is that it's not that your subplot will be square, but that the distance for the units in the x and y direction are going to be identical. So 5 units in the x direction will be equal to 5 units in the y direction. So you see that was the case here with ax.axis equal. You have the tight, and you have the normal auto-scaling. Yeah, actually, yeah, I'm sorry. So ax.tight for tight is not so much that you have 0 margin, but that it will, it won't, the auto-scaling will try to make so that the limits are integer limits, whereas tight, it will make the limits be whatever the limits of your data is. So it's a subtle, subtle difference there. All right, any questions on that? All right, some other things I like about setting limits. So let's say you know that your plot should always start at 0, but you want to let it do whatever the maximum of your data is. You can do that. You can say set y-lim bottom equals, in this case, -10, and set x-lim, you want the right of your x-axis to be 25. You can specify one or the other. You don't have to specify both limits. And note that I am doing this setting of the limits after the plotting. I'll show you why in a moment. Because once you call set x-lim, set y-lim, you turn auto-scaling off. So you want to make sure that you keep that you do this stuff afterwards. So here we see that we have the y limit -10. That's great. That's exactly what we wanted. So everything looks great. Now let's take a look what happens if you do set y-lim, set x-lim before you're plotting. Yeah, not what you want. Because what the y limit here is 1. Well, the default limits, if you're not plotting anything, is 0 to 1. So once you set y-lim, set x-lim, you're turning auto-scaling off. It's going to use whatever the limits are that it knows of at the moment. And so it fell back to the default.
One quick interjection here, just to mention something, if it's all right. The place where this is really, really, really useful is bar plots. So you want the bottom to be at 0 in a lot of cases. You're making vertical bar plots. And by default, the auto-scaling will choose, a lot of times reasonable limits, but you want maybe centered. So you may call margins and it's okay, you get a little buffer around everything, but you really want that bottom to still be at 0. So a really common kind of recipe is you plot a bar plot, you call it ax.margins, 5%, whatever it may be, then you call set ylim and just put the bottom at 0, and you get a nice centered bar plot as opposed to trying to pick integer values. So it's a really common question is I've got my bar plot and shifted it over here to 0 to 10, but my data goes from 0 to 9, you know. That's a quick way to make everything centered and kind of
Right.
Sorry.
Right, because you want the padding for bar above
Yeah.
the bar,
And
but you don't want the
sides.
padding below it.
Yeah.
Right. So another feature not shown here in the notebook, but do we have any meteorologists in here? I'm a meteorologist, so in meteorology, we tend to work in pressure units for vertical coordinates. So 1,000 millibars at the surface, and then pressure goes to 0 at the top. Well, there's no reason why your data your y coordinates have to go in ascending order. If you say set ylim parentheses 1,000 comma 0 in that order, then the bottom limit will be 1,000 and the top limit will be 0. It will do it in the order that you gave it in. And so you can actually reverse your plot, in a sense, that way by setting these limbs in opposite directions.
If you wanted, I guess it's the margins that create more steps. If you wanted to have, more dashes or doing, what does that?
You mean more ticks?
Yeah, more ticks.
Yeah, so there's, we can talk about it in a second. There actually is a second control we're not going to talk about, and that's locator params. I can show you later. There's a way to do it automatically too.
Next, the next L, legends. So what is a legend? A legend shows labels of your data. And so we saw how to label our plots with titles and label our axis with, X label, Y label. You can even label your color bars. You can do that. Well, what if you want to label your data? Well, a quick and easy way to do that is you can actually, while you're plotting, say ax.plot, have that, and then you have an argument label equal some string. So I have here, I'm plotting some temperatures, and I'm going to plot for Philadelphia and Boston. And I'm also then going to do ax.legend with no arguments. And whew, look, I got myself a simple legend, and it took the labels that I gave when I did the plotting, and it helped make that legend for me automatically. By default, the legend will go in the upper right-hand corner. However, you can actually specify other locations, so you can actually say, if you go to the documentation, it'll show that there are different locations that you can specify, but you can also specify best. And best will try to figure it out. It will try to figure out where there is no data and put the legend there. Nifty little thing I like. So there, it moved the legend to be over on the upper right, left-hand corner. Also note that there's only one item in this legend, even though I'm plotting two things. If you want something that you're plotting to not show up in the legend at all, you do label equal underscore no legend underscore. So if I took this out and ran that, oh, that's right, that was something new. It used to be that it would still put that in there, but it would just put in an empty entry. But now let's say I just have that. I guess we test for emptiness. There we go. So it used to be that that would just show up like that, and you didn't want that there. You can say underscore no legend underscore, and that will work like that.
Is there a way to get your legend outside the data?
Yes, I will not cover that right now, but you can do fig.legend, but then because the figure doesn't know what to build the legend out of, you have to then manually tell it what to build legend.
You can also do ax.legend. You just use it. There's a control that lets you
Yes, you can do that too, yeah. Basically, the answer to just about any question you guys have here is, if you ask, like, can we do this? The answer is yes. It's just a matter of by how much pain you want to go through. So we make some things very simple, and then we make pretty much anything else possible. So because we're pressed for time, we're going to skip this example. All right. What time do we have to? I forget when it ends.
11:30, is it noon or is it 11:30? 12, okay.
Sorry, we have to noon?
Yeah.
Okay. So basically, how would one have made these two circles with the legend, and note that, you know, we got the data coordinates be equal, things like that. Go away, I don't care about my updates right now. Solution. So we have our data that we're going to plot. We have our subplots. Well, we're going to have a single subplot, and we're going to have a label equal inner, label equal outer, set our line width, x.axis set to equal, and we're going to set the margin to be about 5%. And indeed, we will reproduce that figure, like so. So if I were to have increased that margin, let's say, to 25, so you increase the padding a little bit. It's not an exact science because you still specify that you want your axis distances to be square, or to be equal, so you're trying to make things still fit. So it tries to merge all that sort of information together to something useful, but
What margins really does is it says it can never get closer than X amount. They'll still try to auto-scale, but it won't let it go any closer than 5% of the maximum width of the data. So it'll auto-scale like whichever axis is the minimum. So it actually will try to fit, you got equal here. It's fitting the Y and then auto-scaling the X because that's the one that's constrained. That makes sense. If both are unconstrained, it'll do exact padding. If one's constrained in some way, in this case the axis equal, it'll do whichever's the minimum.
okay.
Your data is symmetric, right? What, isn't it? Isn't it, are these circles?
So yeah, are you trying to plot it and you're not getting circles? So,
Except without the equal.
yeah, exactly. So that's the, sorry, go ahead and finish.
Why is it not a square if it's?
So if you don't specify AX equal, the X and Y axes are completely independent. So it may put, 10 units to the inch in one axis and 5 units to the inch in the other. And so by default, it'll just try to fit it in the square it's in, and it'll shrink the X and Y scales to match. And so that equal actually just says, make the scales identical. And that's what's not with the constraints too, but yeah, so if you leave it out, you'll get, sorry, I didn't mean to jump in over.
No, but that's a very good point. That's a very good reason why you have things, you have these options available, because, for some, the default behavior, this is what the default behavior produces. But, for some people, that's not what you want at all. And so a very simple call to axis equal, makes it look exactly like you want it to be. This should be familiar again to MATLAB people. Axis equal, is a common call. All right. So now we're going to talk about what goes around the plot. So we haven't really been talking about this too much, but I've alluded to it a few times. We have, these ticks, but what makes them tick? So first thing first, we got to know what are the individual. A lot of questions come up on the mailing list, and people are getting their terminologies all mixed up, and it becomes a major source of confusion. So let's just get it straight. A tick is the location. A tick line is the actual mark. A tick label is the text that goes with that tick. And then a ticker is what determines the locations of the ticks.
This is why naming is hard in anything. You want to have the same name for bot things, it's the only thing you can call it.
Yes. So you're going to locate, so when you have it, so a lot of these things you don't actually have to play with, but we have a ticker by default that will, given the limits that is told, will try to pick out limits that produces integers and will produce between 4 and 5 ticks within that spacing. And that it will try to do it between 10, 1, 2.5, 5. It's rather magical, but it actually works fairly well. I'm really surprised by how well it works. So there's that default ticker that tries to pick for you ticks that make sense, that produce about 4 or 5 ticks for you. But you can override that anytime you want. And so that determines what the ticks are going to be given the limits. And then it will then assign, it will make a label for each one, and it will put a tick line in each one. And that those are going to be the and determine those locations. So you can mess around with the parameters of these ticking with the function called tick params. So what we're going to do is we're going to do an example. We're going to actually go right down to the x-axis function. So we're going to show the 2 ways to do this. So you can go down to the x-axis object. So notice AXIS dot set. We're going to set which ticks are going to be dealt with. So we're going to put ticks at 1, 2, 3, and 4. Those labels are going to be whatever label we want them to be. So we're going to label it 3, 100, -12, and foo. It can be anything we want. By default, it's going to be the actual value of the location of the tick. But I could say it could be anything I want it to be. So that's how I'm going to mess around with the x-axis ticks. Now for the y-axis, we're going to use tick param. I could have done this either way. Y-axis, I'm going to say the axis equal y. So I'm specifying which one I'm talking about. And that the direction is another argument that I can deal with. You can have in, out, or in, out. And so by default, all the tick lines are pointing inward, but you can have them point outward if you want, or you can have them straddle the line. And then you also say what the length of those ticks is going to be. So we want to say that the length, in this case, is going to be 10 points. And let's take a look what that produces.
If we wanted to make one of the axes logarithmic or something, we just change the tick's value?
No, that's the spine.
Well, yeah. And also the scale. The log is the scale, actually, which we haven't really talked about.
Oh, you talk about, okay, yeah. Yeah, that's log scaling, or that actually kind of goes back to that transform system that I was talking about, but you don't have to deal with transform. All you have to do is say, you can actually say a set x scale, and then in quote log, set y scale, quote log. You could say that, and there's a whole bunch of different scales. You can do semi-logs, you can do a whole bunch of different ones that I can't seem to recall off the top of my head right now, but they're all available. So we see our, we see now we have the y ticks, the line straddles the spine, and the x ticks, I have 3, 100, -12, and foo. It's whatever label you want them to be. And then, see, even as I pan it around, it all moves with it. Okay, So how do I do non-numerical categories? So kind of hinted at this with that foo. Let's say you want to plot out quantities of fruits. You can fake the label in a sense by saying that that the data at 2 is going to be apples, the data at 3 is going to be oranges, the data at 1 is going to be peaches. Why?
Those are actually the heights.
Oh, I'm sorry, yeah. There's 2 apples, 3 oranges, and 1 one peach. So, and then I'm going to say that the x tick equal x, which is the, remember, the locations. So ticks is the location, so it's going to be 1, 2, and 3. 0, 1, and 2. Sorry, and that x tick labels equals the list of fruit. And so with this graph, I have now proven that you can indeed compare apples to oranges. So, but that's how you get that. Now, Matplotlib, you think that's rather awkward to be doing plotting like that. The point of Matplotlib is it is the base level plotting library. If you were to use, for categorical data, things like that, you really want to be using something like pandas. And pandas builds on top of Matplotlib. And so it hides away a lot of the messy details like that and will automatically label those bars for you automatically, and you don't have to set all that. But the point with Matplotlib is you can do any of that. So there may be other libraries that build on top of Matplotlib that make some of those steps easy. But with Matplotlib, you yourself can directly control any of that stuff you want. So does that example make sense? All right, now let's talk about another aspect of layout, and that is the spacing. So you're doing, so a lot of these plots where you just had a single plot, you didn't really care too much about spacing, but when you have multiple plots up, you really care about spacing to make sure that things don't run into each other. And so we have a default set of spacing. You could say what the W space is, so the spacing in the width, the H spacing in trying to get this right. Is it W? Why do you call it W space?
Width space and height space.
Height space. I'm thinking horizontal space.
Yeah,
right.
yeah,
So width space. So W space is width space. H space is height space. So spacing and height. Then you could say how much space you want on the left, how much space you want on the right, how much space you want at the top, and how much space you want at the bottom. And these are all in fractions of the figure space. So you say you want the top to be, you want the top of your subplot to go all the way up to 0.9 in figure coordinates, and you want the bottom of all your subplots to go down to 0.1. So it takes up 80% of your figure height. Things like that. And now you got 4 very well spaced plots. So now, what happens? A common thing is that these axes aren't aware of each other by default, and so what often happens is this: is that you got yourself multiple plots, and you got X labels for each of them, you got titles for each of them, and they all run into each other. I mean, that's horrible. You'd never put that in a publication, right? And you go, oh, stupid Matplotlib, what? I can't do it. You can fix it. Now, it used to be that you had to manually specify the spacing, but we have added the tight layout feature, which will try to adjust, given the sizes of your titles and labels and things like that, it will try to adjust everything so that nothing overlaps. And so in that example above, I had commented out big.tight layout. Ta-da! I can send that off to a publisher. That looks nice, right? It's magic. So that's what you, so if you ever run into that sort of situation where you got labels that are overrunning each other, just call tight layout when you're done, all your plotting, and just right before you do the show, you do tight layout, and everything will just adjust and give you appropriate amount of spacing.
What if people are like resizing images?
It's resizing the axes, so it's not going to change the size of any of your labels. So it's not going to change the size of any of your fonts because it's going to assume that that's what you wanted. So it's going to adjust the spacing so in between the axes. I don't think it adjusts the spacing around the figure, so I think it maintains the top, right, left, and...
No, it actually does change.
Does it adjust those? Okay, it adjusts those.
The key thing is it only does it once. So if you start resizing that figure, it generally, you're going to have to try, but you can make cases where that title, for example, will overlap that X label. So if you play around with it, the big.type layout does it at the time you call it, it will set them. But because this actually has more to do with the way text rendering is handled, figuring out the exact extent of text in Matplotlib is pretty slow, so it doesn't do it every time the figure's resized or anything. You have to manually tell it to. So it will do it once, and you could, if you work at it, you can make them look bad again.
Well, mostly in a GUI application.
Yeah. And the key is there, if you want to make sure it does that every time, there's a couple things you can do. One is usually when you're doing that, you have, usually you have some other constraints you're working with. Usually you'll have like maybe 2 axes side by side, so you've got usually some more complicated layouts. There's some other tools that handle those. But the key thing is, at that point, you may just do it. Every single time, you just have a callback when the figure's resized and just say, do it. It's called big.type layout. There's also some other things you can do at a little bit lower level. But you can put a callback on the resize of it and have it automatically do that.
That's actually probably going to be a feature that gets added when we revamp the toolbar system. It'll be a button, tight layout, and it'll just, yeah. The key thing is that it keeps the figure size, because that's considered to be fixed. That once you set up your figure, that's going to be the size of your figure. Although we do have ways to change the size of the figure after the fact, but that's a little specialty thing. But there's that. All right, so all these examples of subplots basically show a regular grid of subplots. But what if you had a need to show, let's say, 2 subplots at the top, but then 1 long subplot at the bottom? Then the subplot mechanism that we have here will not work for you, but because it assumes that equal size subplots and things like that, which satisfies 99% of the needs out there, but you're not left hung up and dry. You have there's the mechanism that's under the hood of the subplot, and that is called grid spec. And what grid spec does is that it allows you to specify more complicated grids of plots. And so you can say that first row is going to have 2 plots, but then the second row is going to have a plot that is 2 wide, and then maybe a third row is going to be 3 plots or something like that. You can do more complicated structures like that. There's a whole documentation for it online. I'm not going to go over it here, but if you need more complicated things like that, it's called grid spec. All right, so the question that came up to me earlier was, let's say you have multiple plots and you want it to be so that the limits of those plots are always the same. That's called sharing your axes. And so, like, we talked about the autoscaling, and the autoscaling, it works off, it will autoscale for the data in that axis. But if you say that I want to share the x-axis of the 2 plots, or I want to share the y-axis of 2 plots, 2 subplots, or 3 or 4, or however many you want, you can say, it will then take into, autoscaling will then take into account all of the data across all of those things. Or if you manually specify the limits to any one of them, that will override the limits for all of them. So here in a situation, we're going to say share x equals true, share y equals true. We're going to create two subplots, and these all have different limits. And it's going to come out that they will share the limits. Also, when you do this share x, share y through plot.subplots, it will automatically take away unnecessary tick labels.
What if I don't want them taken away?
You can turn it back on. You have to go in manually. There's also other ways that you can specify axis sharing that it doesn't do this sort of magic for you. This is the easiest way to specify sharing, but there are other ways. So when you create, you can when you create any axes, you could say that it shares the x's from this one and things like that, and that one doesn't do any sort of magic. So there are multiple ways, but the concept is called sharing. And now, also note, and this is the question that you had, I'm going to pan. No oohs and ahs? Yeah, they both move. If I zoom, they both move. I love that. I use that all the time because I'm typically plotting things like radar reflectivities and then Doppler velocities. I'm panning in one, or I'm zooming in on a tornado here. I want to see the Doppler velocity matching that. So I don't want to be having to zoom in on both of these things. So it will take care of it for you automatically, interactively, all that wonderful stuff. And also, you don't have to set the limit each and every single time. You can wait until you're done, and it'll figure it all out for you. So I just like that. Another feature that typically gets asked for is, let's say you want a single plot, but you're plotting two very different things on it. It's called twinning your axes. And you'll see what it is in a moment. So let's say I have data in one scale here from 1 to 4, and I have other data that is meant to be shown with it on top of it, but is on a completely different scale. You're plotting it like it's two axes. So I have ax1.plot, I have ax2.scatter. But I called ax1.twinx. And so what it's saying is that you're going to twin up the x's so that the x-axes are going to be identical, but the y-axes will be independent of each other. It'll be different. And you can also do the same thing using twin y. So you can say that the y-axis are going to be the same, but then have different x-axes on the top and bottom. So, and then interactively, I'm panning this around. It moves both of the axes for me. So everything all stays together. Again, this is also a great example of the transform stack, is that I have a single subplot here, but the transform stack knows where to place everything, even though they're concurrently sharing the same area. So again, it's another great example. All right. Any questions on those two? So there's the axis sharing, and then there's the more specific feature that is the twinning of axes, so that way you can have them on top of each other.
Is twinning limited to two different axes?
It doesn't make any sense to be able to twin both x and y at the same time.
You can't do it, though. And it doesn't make sense in some cases. Sometimes you want to show data that's completely independent of scale but have it overlaid. If you want, I can show you an example. But it's actually not. You can chain the twins and have like 3 or 4 y-axes, or have both independent x and y-axes and have 5 or 6. It's possible.
Yeah.
It starts to get ridiculous after a point, but you can do it.
Yeah. But it's a matter of how much pain you want to go through.
It's actually-
I will show an example called parasite axes. That way if you have, let's say, three axes you want to show, twinning is only 2. But if you need 3 of them, that's when you start using something called parasite axes, where you can have another axis be a parasite of a host, and you can build on and on. So you'll see an example of that in a later section. So then there's something called spines. Your axes have spines. So by default, you do see spines. There's the bottom spine up here, the top spine here, the right spine, and the left spine. So it forms a box. And so you think it's actually one polygon, but it's actually 4 separate lines. And so we can mess around with those spines so that it looks different. And so this is actually a styling thing that different publications want their graphs to look a certain way. So let me just show an example of something you can do. Don't worry about that warning. So a lot of publications, they don't want your plot to look like a box. They want it to have their spine offset from each other. You can do that. So in this example here, I set the top spine to be turned off, so set visible, false. The right spine I also set to false. Also, the spine is independent of those tick lines, so I also have to tell the tick at the to only be on the bottom and on the left. Because if I don't do that, yeah, the spine will be gone, but you'll still see the individual ticks, or the tick lines. And then if I want, let's say, the spine, the left and the bottom spine to be out a bit from the plot, I can say that the bottom spine and the left spine, I set their position be outward by 10 points. And that's the example that you saw. Now let's take a look at a different way I can do it. So let's say I want to have the spine to stay intersected. I don't want them outward. I want them to intersect at 0, 0. By default, the spines form a box always. But some people may want it to look like graph paper and to have the spines intersect right there. Well, you could say that the bottom spine and the left spine are at data coordinate 0. Data coordinate 0. Again, the transform stack. Ta-da! Yeah, you get the 0, get the lines in. When you start doing things like that, we can start messing around with making those ticks just disappear. We can get rid of those ticks if you want, things like that. Now, what if I want the one thing you'll notice with the spine being at 0, 0 is no matter how I move it, that whole thing moves, right? What if I want the spine to always be at a particular location in axis coordinates? You'll see what I mean in a moment. So I'm going to say that the bottom spine is going to be at 75% the way down on the axis, and that the left spine is going to be a quarter of the way horizontally. Ta-da! And now, when I move, things, those spines are going to stay right there. But the coordinate system moves. So you just saw 3 different ways that I can mess around with the spine to get the desired effects that we want. And you can control these things independently. And you got 4 spines that you can mess around with. So you can set the bottom spine and the left spine to follow things in data coordinates, but then have the top and the right spine follow things in figure coordinates or in whatever. You can do that if you want. All right. This is a nice example. This is the last example for this section, and then we'll take another quick break. We're going to try to reproduce this figure. So what's important about this figure is that you have yourself 2 subplots. So you know you're going to have n rows equal 2. They're also going to go right up against each other. So there's going to be no spacing in height. So h space equals 0. They're also going to share the same x axis. So you know you're going to be sharing. I think that's the main. Oh, and we also turned off the tick lines on the right and on the top.
Finally, there's the spine at 0. The spine's at 0 on the top one too. That's the final thing.
Right, and we set the spine at 0. Although we could have done AX H line, right?
But then,
Mm-hmm. Oh, right, but then that's how you get the tick lines up here, right, and the labels. Okay. So there's a lot of stuff to think about there. Let's go right to the solution. All right, so we got the data. So friendliness and popularity. I'm surprised cat even gets any friendliness at all. I really like that Geico commercial with the cat just leaves him in the desert. Go get help. Meow. So we're gonna do the same thing. We're gonna do very similar things twice. We're setting up a bar plot. We're gonna say that so something we didn't cover bar, that by default bar, if the coordinate represents the corner of the bar. So this throws a lot of people off. So if you say a line equals center, then the coordinate means the center of the bar. And so we're setting the ticks. So the tick location is going to be 0, 1, 2, and 3. Tick labels are going to be the names of the animals, and the Y labels we already will be passing in, which the Y labels are going to be the data values. So the x-axis, we're setting position. We're saying that there are going to be ticks only at the bottom axis, and we're going to set tick positions only on the left. So we're getting rid of the ones on the top and the right. Tick params, we're going to say that the x ticks, the lines are going to go in and out. So they're going to straddle the spine, and they're going to have a particular length. And we're setting a margin, just to keep things nice and tight. Subplots adjust. So we covered that function. We're going to say h space equals 0. That way, the 2 plots are going to line up right on top of each other, right next to each other. And then we're going to plot the 2. So it was actually rather simple. We're going to do the 2 plots. We're putting them all up right next to each other. We do the bar plots. We set the tick labels. We got rid of the top and the right ticks, and we straddle the tick lines. And we also set for the bottom spine to be at data coordinate 0. So it happens to be the bottom for this plot, but it's in the middle for that plot.
So one of the things, I wrote this example, partly it's a complicated one, but it was to show everything being non-default. So how do we want to change basically a lot of different things? So it's meant to be kind of a complicated example to give you some sense of how to change a lot of things that you might want to change around kind of the borders.
Mm-hmm. the point is, you can control anything you want with this. So let's say you wanted, I think you could do like tick labels to be on top. You would use the top spine, and you could do things like that, and you could control a lot of crazy things like that. All right, let's take a quick breather, get back, and we'll get over to the last. We'll just power through the last couple sections. The last couple sections, I guarantee you, they're really short. So just to spend 5 minutes. We'll be back at 12:20, 11:20. Sorry, I'm still on Eastern time. All right. Well, let's just power on through. So these last two parts, we're going to power through, and I guarantee you, we're not going to get ourselves bogged down in this. They're more intended to be showcases. We're now getting to the more advanced aspects of Matplotlib that I'm showing it here just so that you get a general understanding, not that you become proficient, but you get a general understanding of, it's kind of like, I'm not an auto mechanic at all. But, I lift that hood up in the car and I go, well, that's an engine. I know not to touch that thing except to fill it up with oil every once in a while. But you're not going to expect me to do anything. But I know that that's the windshield wiper fluid, not the transmission fluid. So make sure I get the right oil in the right place. That's what this next two sections are going to be about. So that's what we're going to do. So artists, everything in the past 4 sections, anything that's visible is technically an artist object. If you guys here already understand object-oriented programming, basically everything subclasses artist. So artist, anything that can be drawn is an artist. So you too can be an artist. No, you don't have to be Pablo Picasso or anything like that, but you too can draw. So we have a bunch of standard artist objects that basically form the primitives of Matplotlib. And this is just kind of shows what they are. So it's actually a little bit more complicated than you would think. So we have ourselves a wedge is one type of artist. We have arrows, line 2D, because there's also a line 3D elsewhere. We have rectangle, ellipse, fancy box patches. Fancy box patches lets you do rounded corners and things like that. Circles, polygon, arbitrary polygons. You could do patches that follow arbitrary paths, things like that. And then also another artist that you might be completely missing here is the circle. I'm sorry, the text. The text that are underneath, each one of these are all artists. Anything that is visible here is an artist. And heck, there's actually a few artists here that aren't visible that you're not seeing because it's the background. So that's also an artist. Everything is an artist.
You've used the word patch before.
What?
How does patch fit into this? What is patch?
So patches are basically just filled, either polygon. They don't have to be polygons in general, so they can have curves and stuff. But it's a filled
Region.
Yeah.
Yeah, I have actually personally asked this question on the mailing list because I've never totally understood the difference between polygons and patches. But yeah, if I remember correctly, yeah, patches can have an open edge, right?
Well, and two polygons can't have Bezier curves, can they? Which
Yeah.
patches can.
I can't remember.
Okay.
I honestly can't remember. There is subtle differences, but and so those differences are important, but
Patch is the more general. I remember that much for sure.
yeah, patches are more general. You can do more things with patches, polygons. There are certain assumptions that are made. And then like some of these different artists, they're constructed differently. So for example, a circle, you could have represented a circle with a polygon or whatever, but with a circle, it will always be a circle, no matter what your aspect ratio or whatever, because it's defined to be a certain radius away. Meanwhile, if you wanted something that was, squashed or something, you would use a path patch and specified all the vertices, so that way in data spaces, all that way. The other nice thing with like circle is that as you zoom in, depending on the transform system that you chose for it, it may decide to stay exactly the same no matter how much you zoom in. So if you notice when you do scatter plots, as you zoom in, the size of those markers don't change. But those markers are all drawn the same exact way using these artists. They just simply chose to be in a different level of the transform stack to indicate its size. These are complicated things. This is just meant to be a showcase so that you understand what sort of the possibilities are.
Bezier curves is the difference.
Yeah. Right, still. So then, those are the artist primitives. Then there are containers. And containers are artists that, contains other artists. So two right off the top of the bat are figure objects and artist objects. So this is how we have the hierarchy, is that figures contains axes. They can also contain some other things as well. You can attach other artists to a figure, but then those axes objects, they contain other artists to display. And so if you think about this for a second, you can actually create your own plotting function. All the PyPlot functions do for plotting are just simply sucking in this data that you provided, generating all these artist objects for you, and then adding them to the axes, and then modifying any of the appropriate properties. So that's all those plotting functions do. So you can actually create your own specialty plotting functions that do not use any of PyPlot's stuff. You can actually create your own crazy stuff that works with these primitives to your heart's content, that will satisfy your own particular needs. So let's take a look at one particular example. We're doing plot.plot, and it's going to return back to me two line 2D objects. So plot.plot returns a list of line objects. In this case, I'm doing 2 lines, so it's going to give me a 2-element list. And I'm going to set one of them to have a line width of 5, and I'm going to set the other one to have line width of 10, and to be slightly transparent. I'm setting its alpha value. So you see I made the first line here, went up here. Remember, it was plotted first, so it ends up underneath the red one, because that was plotted second. But
Why is the first line of code in that example necessary? Can you scroll up a little bit?
First line.
The figure, why did you create the subplots?
So you have to create a figure in axes. If you're using the plot directly, it'll do it behind the scenes. But if you're not, if you're using the way we've been doing it for most of this tutorial, we explicitly say I'm going to make a new figure and I'm going to make an axes on it.
yeah, so I could have just as easily done this.
But technically that first line is not necessary, right?
The big AX equals plot.subplots?
Right, yeah, so I could have also done.
It is necessary unless you use.
Yeah, because we're talking about a single figure, single axes, yes, I could have also done this.
The problem with this, though, is that if you have another part down the way,
I'm just curious.
yeah.
Yeah, but this is what I was talking about back in the beginning. with the implicit versus the explicit mentioning is that, sure, the implicit thing may be simpler, easier to follow, and is really good for short scripts or even just typing right into the REPL, the Python interface, but it's not explicit. And so when you start having multiple figures and multiple axes, it gets confusing about what it is you're actually referring to at any given moment. So that's where the difference becomes.
The big thing is if we hadn't called show and we called plot again somewhere else, it actually won't create a new figure and put it on that same figure. And so that's why we've been kind of stressing that make a new figure, a new axis each
Right.
time, so you're clear
Because
about
there already existed a figure. Right.
So otherwise you can wind up, why is it on this old figure? It doesn't make any sense, you know, that's why it's the kind of implicit.
So I mentioned that the figure object can actually have other artists besides the axes object. Well, one of them is the background patch. And so you can access that with fig.patch, and we can find out what sort of properties are available. So it has a whole bunch of, AA means anti-aliasing, ag filter, don't worry. There's all sorts of attributes that you may not even realize exist that can be modified at any given time. And that's how you find out what sort of properties you can play with. So we talked about the primitives. We talked about the containers. Well, then there's another thing that's kind of like a container, but it's not really. They're collections. And what collections are is a collection of artists' object, or at least something that represents a collection of artist objects. So some collections actually are just simply a list of circle objects or a list of whatever. Or other collections are designed to be to optimize so that way it doesn't actually have to hold that many artist objects in memory. It just needs to remember, okay, I got this data here. I'm just going to always render this many things all the time, or repeat rendering, just restamping things. It can do various optimizations. So for example, we have line collections, we have circle collections, we have path collections, we have patch collections, we have all sorts of collections that tries to keep in one place the representation of many, many objects, many artists. The other useful thing about this is that you can then state, okay, I want this collection of artists to be red. Well, you don't have to loop through every single artist and set their color attribute to be red. You could just say once, set color red, and you're done. But then you can also individually modify individual values for some things. So here we have ourselves a line collection. It's going to be 3 lines. So I have a list of tuples. And so the list is, the first list is one for each line. Each element of that list is going to be the list of vertices. Each vertex is represented by a tuple of XY coordinate. So I have 3 that, and then I create this line collection. So I'm not doing plot anymore. I'm creating an artist directly. I'm going to set the color to red. I'm going to set the line width to 5. And then note this line here, I'm going to add collection LC. Getting back to what I was saying earlier with the pyplot functions. The pyplot functions, they are creating these primitives and these collections for you and adding them to the axes. So you don't have to do it yourself. Well, when you are playing around with the artists directly, creating them directly, you have to explicitly add them to an axis.
So what's the advantage of doing this instead of just looping over all of those vertices, 4-item in list?
It's just conceptually. Fewer lines of code.
There's actually one big difference in terms of what happens behind the scenes. In most cases, that's about an order of magnitude faster to draw. So if you're worried about performance and you have millions of lines, putting things that share the same properties into the line collection will really speed up the speed of your drawing. And that's because basically what actually happens, it depends on the renderer, because I don't want to get too far into this, but for most things you're going to use, it actually sends a draw call down, and the collections get passed down as a single draw call instead of a bunch of different draw calls. And so it's
able to just simply stamp things and just repeat the same data point over and over and over. So it uses less memory. It can have a lot of advantages, both just simply semantically by having just a single call there, but then also by going, oh, well, I'm only given one value of this. I'm just going to use this same value over and over and over. So.
Is there anything like arbitrary collections that aren't?
The collections all have to be of the same type.
Some of the types are very arbitrary. Patches are a good example of completely arbitrary types. So they have to share some properties, but a patch collection is about as general as you can get. You can represent basically everything with a patch collection. So, yeah.
Okay, so, and then also note that I'm having to set the XLim and the YLim because the auto scale, well, you could actually do this. You could actually have, when you do add collection, you could have it go through all the data and then figure out auto scaling for that as well. However, just to keep this example simple, I'm explicitly setting the limits for this right now. So you see, I just created 3 lines, and they're all red. Now, let's say I don't want them all red. I want to actually make the first one red, the second one blue, and the third one some RGB tuple. Getting back to the previous section where we talked about how to specify colors, right? And then let's say I want them to have also different line width. So 4 points, 3 points, 6 points. I didn't have to, but I can do that. There we go. Different thicknesses, all that, but it's still the same object. It's the same collection. I can modify some of, you can't modify all of them, but you can modify some of them, some of their individual properties, so that way you can target changes for individual things, but then it can still assume a lot of other things. So for example, they all have the same line style in this case. They all have the same draw style, they're all under the same transform system, they're all under the same axes. So it's able to make a bunch of assumptions and it helps optimize for that. And then there's many other kinds of collections, as I was saying, and different kinds of collections can then make different kinds of assumptions about its data so that it can do certain kinds of optimizations. So another kind of collection is called a regular poly collection. And what a regular poly collection is, it is a polygon with regular sides. So you can say that you want a collection of polygons that have, let's say, 5 sides, so a pentagon. And we're going to make them really big. And the offset, so working with some of these collections to get a little awkward. So we have offsets, that's basically the offset from a central location, or some common location. So you can say that it's going to be at this coordinate, that the different pieces are all going to be this coordinate away from some common location. And then that the trans offset, that's the transform for the offset location, and we're going to say that that is going to follow the data coordinate system. So again, we're kind of bringing together a lot of these things. We're just showcasing that's how there's a reason why we have plot and scatter and stuff, because if you had to do that yourself all the time, you'd be coming at me with pitchforks and fire, because you just like, why should? But if you do need to do something like that, it's available to do that. please don't come after me with pitchforks if I'm not. So there, we got ourselves a whole bunch of pentagons. Pentagons, and they're all organized in random locations. They're all the same size, all the same color, and they all work according to the data coordinates. So as I scroll around, it does this, and then as I zoom in, they're not getting any larger, right? The size was specified in one coordinate system in points, 150 points, whereas, so points is dots per inch, something like that. So many dots per inch, I never remember, I think it's 72 dots per inch, yeah. So that way, that never changes, but meanwhile, the location of it, the offsets are all moving around all over the place. All right, and as an exercise, I want everyone to give themselves some gold stars. And since we don't have time for that, let me show you. We're almost done, I swear. So I created, we're gonna put 4 gold stars, y coordinate 0.5, x coordinate 0.2, 0.4, 0.6, 0.8. Stars are gonna have 5 points. So the offset's what we set there. We're gonna have it set to the data coordinates. Face color, it's gonna be gold. And sizes, let's make them bigger than that. And note that the sizes, face colors, they're in lists. So if, but there's only 1 element list, but I could make it a 2 element list or a 4 element list, whatever. Ta-da! You gave yourself 4 gold stars. So, any questions on these artist collection containers? All right, last section. And this, again, this last section is going to be just a showcase. Oh, wait, I want to leave page. It's just a showcase of the toolkits. So there's a variety of toolkit that extends the features of Matplotlib, but we do not, but they're considered to be outside of Matplotlib core. And there's a variety of reasons for that. For example, the first one here I have listed called basemap. Basemap is what's known as an MPL toolkit. It is being superseded by a new package called CartoPy. However, basemap is still supported. Basemap is for plotting, well, maps and other sort of geographical data. CartoPy is the new generation version of that. That's getting mature and it's getting better and better all the time. But for basemap, it's still around and it still does its job. It's just slightly awkward. But with basemap, the package itself is so huge because it has to package a whole bunch of geographical data. So we don't actually ship basemap with Matplotlib itself because most people don't need that. So you can get basemap separately as a separate package installed, but it's all part of the Matplotlib community. Then there's 2 more toolkits. They are shipped by default with Matplotlib, but because they don't behave quite like normal Matplotlib objects, we don't want to call them standard because they do break in some edge cases. So, or they're not quite right. So we put them off to the side because they're useful, but they don't perfectly represent the standard behavior of Matplotlib objects. So so the second package here called mplot3d. I did not create mplot3d. I'm just this unfortunate soul who's left to maintain it. I just needed it for 1 semester a few years ago. I needed to use it, and so I submitted a bunch of patches to fix certain edge cases, and then the previous guy said, Patsy, it's yours now. And he ran off. I am not kidding you. He basically sent me an email saying, it's yours now. So I've been maintaining it, and I haven't been able to find another patch. So not that I really, it's neat. Matplot3D is a trick to make things look three-dimensional. Unfortunately, Matplotlib core rendering engine is 2D based, so it can make things appear 2D, but it's not quite perfect. And so there's a whole bunch of edge cases where if you want to do something more complicated, don't use Matplot3D for it. But for simple things, it works just fine. And it looks a lot like regular axes. So you can do ax.plot, ax.scatter, things like that. So you can do a lot of nifty stuff. But then it also adds a few additional ones. So here's an example doing a wireframe plot. Whoop. Oh, I forgot to do the first. Oops. But look, you got yourself something that looks 3D. And then you can even click and drag and move it around and do all that other sort of nifty stuff. Works great. Wonderful. The thing that gets really complicated, if you were to add stuff to that plot frame, you get what I call Escher effects. You know that artist Escher who drew like those sort of visually impossible, like physically impossible scenes, like with the staircase where everyone's going up the stairs, but they all linked up to each other and stuff. You get Escher effects where because it can't layer things properly, things look to be in front of other things when it really is behind or in the middle. So it doesn't look great. But for simple stuff, this works just fine. And so that's what it's useful for. Then there's this other toolkit. I love this toolkit, Axes Grid 1. It's called Axes Grid 1 because there was an Axes Grid toolkit, but it had so many bugs and stuff, we had to rewrite it. So we created Axes Grid 1 as a replacement because we didn't know a better name. It can do so many things, and I really encourage you to go to its documentation page because it's really awesome.
You're asking about how to keep the color bars the same size.
Yeah,
That's the answer.
and stuff like that. It's just really just awesome. But I'm going to show an example. So one of the things that happens when you're dealing with color bars in normal Matplotlib is that the color bar steals space from other axes. So the layout may not be quite what you want, the sizing may not be quite what you want. Here we have an example where we have now 4 subplots that all share the same, so share X and share Y is all set for them. They're all spaced nicely, and the color bar spans the plot area very nicely. And this was all done with a single call to Axes Grid. And so you say that the C-bar mode is single, so you just want a single color bar. You say the C-bar location is going to be at the right. Label mode is capital L. And so label mode, so notice that the tick labels are here on the outer. So you could also have not specified that, and so you still get all the tick labeling all over the place. You can specify how much padding is in between the axes. You can say that they're going to share all the X's and Y's. So just to kind of give you a sense of what would have happened. Let's say I wanted the color bar to be at the bottom. Really, really simple change. It automatically changed all that for you, and so that made things just automatically, just makes that sort of stuff very, very simple to deal with. So And then there's this other feature, not exactly quite sure how to describe it, but we were getting into that a bit with the twin X and twin Y. It's called parasite axes. And so there I have a third Y-axis here if I needed to off of the main plot area.
It is actually pretty easy to do that with twin Y.
Hmm?
It is actually pretty easy to do that with twin Y. You don't have to use pairs anyway this time.
Well, but Axis Grid 1 was the one that did it first. I think then they made some additional changes because the spine stuff came later.
Oh, that's right, yeah.
The spine stuff came later in like version 1.2. And so Axis Grid 1 was around since version 1.0, so.
Yeah, you're right.
So they did that first. I mean, admittedly, the code is a bit complicated, but it's also doing a lot. Then we have this other thing. You can't do this in the regular Matplotlib, called floating axes. Give it a second. Did it run? I was having problems with this one yesterday on the airplane. I get this one to sometimes run and sometimes not. I don't know why. Again, this is one of the things why, this is part of the reason why it's out in the MPL toolkits, because it's just sometimes, let me restart the kernel. I can get it to run if it's the first thing I do. And I don't know why. Yeah. But yeah, you can do things like this if you wanted to. You know, have really fancy looking plots that are very specialty type designs. You can do it with actually Grid 1. So, yeah, I mean, and these things work. You know, well, it does it in odd sort of ways, but there's, again, this is like one of the reasons why it's not in the normal Matplotlib, because, you know, me panning and zooming, it's not doing what you would normally think it'd do. It's basically making a fake set of axes inside of the main set of axes and just turning off all the main stuff and doing its own thing inside. So, you know, messing around with things like that, it's not going to do what you think it does. But, you know, it makes, if you needed to make your plot look like that, then that's how you do it. So, and all that. And so that is the teaser of the MPL toolkits. And these are just the 3 toolkits that I'm talking about here. There are actually so many other toolkits. They're not officially toolkits, but they're very, very useful tools that build on top of Matplotlib. There's Seaborn, there's other certain, they all exist and they're all fantastic. And I'm just so stoked to, you know, to see you guys come and learn all this stuff, be a new generation of Matplotlib users. I'm so happy that you guys are here, and thank you for listening.